After that, the next category is what happens when cables reach end of service, and cable recovery from John again. Cable recovery 101 from Michael Logan, and recycling, reuse, sustainability from Dr. Mike Clare from NOP. Then the workshop closes at the end of that category. So going on to the first category, repairing cables when they are damaged. And the first presenter is Matt Hart from Biggs Marine on power cable repair. Okay.
Is it possible to get like the red dot?
Yeah.
Oh yes. Yeah. Sorry. Perfect. Okay, my name is Matthew Hart. I'm operations manager on the cables team at Briggs Marine, and I'm going to run through doing power cable repairs. I thought this photo was quite a good photo to get a feeling for some of the challenges you have for working on cable repairs. So this is us removing a cable from a wind turbine, and typically the J-tube, which is where the cable goes from the seabed and up into the wind turbine, is below the waterline. And here it's actually in the splash zone. So these are divers, not doing very much diving, installing rigging onto the J-tube so we can actually get the cable out. And in the background, we've got a barge which has got the cable repair spread on. And we decided to use a barge here because the water depth's very shallow. I'm going to go through kind of potential causes of faults, emergency preparedness, key challenges that we have when we're doing a cable repair, different vessel types that you might use, cable jointing just to kind of look at what they might look like, and then recovery operations and installation operations. So potential causes of faults. So it could be installation error. So it could be overbending. So that's where you bend the cable beyond the minimum bend radius. And in this image in the bottom here, you can see that cable is very bent. And don't worry though, this is the cable we're removing. So it's an old cable, not one that we're installing. So you wouldn't normally do this. Overpulling. So on the right hand side, you can see we've got a J-tube here and we've got the cable coming out and going down onto the seabed. When you pull the cable in, maybe there's a blockage in the J-tube. And when you're pulling it in, maybe there's you overpull the cable, you put too much tension in to try and pull it up the J-tube. Also just damage. So that could be something getting dropped on the cable when you're installing it. It could be that there's a sharp edge on the cable repair spread that damages the outside of the cable. Now, what I will say is we do a lot of engineering, analysis and planning to make sure installation errors don't happen. And so they're quite rare. The same with, we do a lot of analysis and engineering on the cable design as well. So cable design, static versus dynamic cables. A lot of the cables we install are designed to be static. So that means that they're on the seabed or they're in the J-tube or they're going up the beach and they don't move. And that's what they're not designed to move around with the wave action. However, you can see here on the J-tube, where it exits the J-tube and it goes down to the seabed, it's actually in free space in the water. And that's a dynamic environment because you've got currents acting on it, you've got wave action, you've got swell. And in order to counter that kind of movement of the cable, you have cable protection systems and they clamp around the cable and they protect it from anything hitting against it, but they also protect it from moving around. CPS design though, say the CPS the cable protection system gets damaged, then it could fall off. And if it falls off, then the cable's no longer protected and it could move around. And it's in a dynamic environment, not designed to do that. It could fault. You kind of touched on this yesterday as well, but temperature. So in the cable design, you need to design in that's going to be at the right operating temperature when it's buried, and you have to take all that into account. Environmental conditions. So currents can be acting on the cable, so we bury them. Or there could be wave action, and there could be swell as well. And then a big storm comes through, and it can move the seabed, and that so that could cause a fault as well. Third-party interference. So this is a big one we kind of already spoken about, and so that could be anchors or fishing gear acting on the cable and hitting it and then damaging it. And then human error. So we kind of saw yesterday, there's a lot of cables getting installed all around the world. a lot of wind farms going on, and that kind of stretches the experience and the competency of the people. And really, that's why we have these workshops that we're in right now, is that we want to bring in new people, get the right experience, so we don't have that issue of competency. So emergency preparedness. This is more related to the asset owners, so the clients that we work with. So they may do testing on their cables, and they might identify that one of them has a slight issue. So they might plan to repair that cable before it has a fault. The reason for doing that is they can then plan that in around other maintenance or they're doing on the cables or on the substations or on the wind turbines, and they can also plan to do it during the summer. And that means that there's probably going to be better weather, less risk, that there's less commercial risk, basically. We also heard yesterday that interconnectors don't need a marine license to do a repair. However, wind farms do. So some of our clients will go and get preemptive repair marine licenses. And what that means is if there's a fault, they can straight away go out and repair that fault rather than having to do an application, wait 14 weeks and lose revenue over that time. We also work closely with clients to do pre-engineering documentation packages. So we will take the information about their asset, about the cable, about the site, we'll plan in what equipment we're going to use, and we'll write procedures, and we'll have them kind of like 75% ready, so that if they have a fault, we just need to get that finer detail, finalize the documentation, and then we can go out and do the repair, and that speeds everything up again. Challenges. Yeah, so kind of touched on cable protection systems. So on wind farms where the cable's going into the J tube, those are designed to get installed, but they're not designed to get removed. So very often we'll find, and this is an image here, where we had to go in with a diamond wire saw and a ROV, cut the J tube so that we could remove the cable protection system, remove the cable from inside the J tube, and then come back down, clamp on a new J tube, new bell mouth, and install a cable. We also have busy cable corridors. We spoke about like interconnectors coming into all the same location, and it's going to be quite busy. And up here in the blue, this is an offshore substation. You can see there's quite a few cables going into it. If you have a fault on one of those cables, you've got to somehow work on that cable without interfering with the cables next to it or potentially damaging them. That takes quite a bit more planning. Water depths. A fault could happen at 40 meters water depth, or it could happen at 2 meters water depth. Have different challenges. You might use different vessels, and you might use different equipment to do each of those. And we'll have a look at those different vessels in just a minute. Seabed type. You might have nice soft sandy seabed. Easy to remove a cable, to debury it, and then easy to bury it again. Or you could have rocky, bouldery seabed like this. Difficult to analyze and figure out how much tension it's going to take to pull the cable out of this, and then also more difficult to bury the cable again. So you might need specialist tooling like the a chain cutter trencher just here on the right hand side. Rock dump. So where a cable has been installed and it hasn't met the marine license conditions of a certain depth, or that's to be buried to, you may need to come back and rock dump it afterwards. If you then need to do a repair on it, it's not too difficult to pull the cable out of the rock dump, but actually burying it back through the rock dump and back into the seabed and to the correct depth can be quite challenging. Vessel types. So here we've got a anchor barge. So it doesn't have any thrusters or anything. It's towed into position, and it holds its position using 8 anchors. In order to move around and lay the cable or remove the cable, it winches in and out on those anchors, and then you'll have to lift and reposition the anchors as you move along the route that you're laying the cable on. You can see the repair spread on the vessel. So we've got a reel here with the new cable. We've got a quadrant and some rails running down the deck, and then we've got chutes at the stern of the vessel. And we'll go through that again in a bit more detail later. Why you would use a barge is it can operate really shallow. It can also ground out. So in some circumstances, at some parts of the tide, the vessel might actually sit on the seabed. Although to use it, you need more planning, so you need more mooring analysis, you need to plan where the anchors are going to go, you need more detailed lay plans, and you might have to do more UXO surveys before the vessel grounding out. Vessel types. Here we've got a DP2 construction vessel, actually the same spread as the anchor barge on the back deck. It's just a much more condensed deck, so it's not as big as the barge. So it's a bit tighter to fit it all on. These work in deeper waters. It might be more like 10 meters or more. Simpler lay planning, so you're not having to move anchors around, and you don't need extra vessels to move those anchors. So yeah, jack-up vessels. Here again, we've got a similar spread on the back deck with the reel with a new cable, but instead of the quadrant and the chute going over the stern of the vessel, it's actually going from side to side, so from port to starboard. Where you might use these, you might use a smaller jack-up, and that might be good for shallow cable repairs, or you might use a big one like this. And the reason you might use a big jack-up is that some of the repairs you do can take 5 to 7 days for each joint. And while you do that jointing process, you need a really stable platform, and it needs to be really weather resilient. If you're doing a repair in winter, the chance of getting a good weather window to do that is really limited. So what you can do is jack the vessel up out the water, and then you're no longer like floating, and you're much more weather resilient. In order to do that, you might have to do additional UXO surveys for the legs penetrating into the ground. Cable jointing. So top left, we have an export cable repair joint. You can kind of get a sense of the size of it with the person next to it. So this one weighs 3.5 tons. The one below is an inter-array cable joint. Inside, they're both very similar, although the export cable repair joint might have a bit of framework to support the cores as they get aligned and jointed together. You can see inside the inter-array cable here. You can see where the cores have been jointed together. You can also see where the fiber optics are being spliced together as well. So in order to do a joint, once you overlap the cables, you need to lift on a jointing habitat. And what that is it's a container basically that goes over the top of it, and it allows you to control the temperature, humidity, ventilation as well. So that's a safe space to do the jointing in. You can also add in lifting points like you've got up here, and that allows sections of the joint to be lifted and slid into position. So now I'm just going to go through how you remove a section of cable. This is kind of a bit of a generic storyboard of how you do it, and then install a new section. So you'll mobilize your vessel, or in some circumstances it might already have a whole repair spread on board. And then you'll go to where the new cable that you're going to be installing is being stored, and you'll load that onto the vessel. You'll then return to site, and the first thing you'll do is debury the cable. And in this case, it's soft sandy seabed, and we're going to use a controlled flow excavator. And that's basically big fans that point down, and they blow water down onto the seabed, and it liquidizes the seabed and deburies the cable. And you'll debury the whole section that you're going to be removing. You'll then locate the vessel to say 50 meters beyond the fault location. And at that point, you'll lower down a grab cutter here, which you can see here. This is a grab with a diamond wire saw on it. You go down, you grab the cable, cut the cable, and you'll recover that end up to the deck of the vessel. What I'm going to do is I'm going to call this the second end to try and not make it confusing. And the reason it's the second end is that is where we're going to do the second joint. So what you'll do, I'm just going to skip ahead quickly, is you pull the cable up and over the chutes on the deck and then load it into a tensioner. And that is a track system that can grip the cable, and you can move it safely backwards and forwards. So you'll load that second end over the chute into the tensioner, and you'll start recovering the cable. And the jointers will strip that cable back, check to a point where there's no longer any water ingress into the cable. And they'll say, okay, this cable's good, it's safe for jointing onto. They'll then test that cable and prove that the rest of that cable doesn't have any issues and that it's good for jointing to. We'll then seal that cable end and lay that back down, which is what you can see here, and you lay it down on the seabed. Once you've done that, you'll relocate to the first end of the cable where you're going to do your first joint, and you'll put an ROV down, you'll connect rigging on, and you'll connect the crane on, and you'll lift that end up over the chutes and into the tensioner. You'll then start recovering the cable in, say, 10-meter sections, cutting it up, storing on the vessel, and that'll go for recycling. When you get to the faulted section, you'll cut that out and you'll seal it and you'll quarantine it, and that'll once you get back onshore, will get sent away for analysis to find out what caused the fault. You'll then continue to recover cable in 10-meter sections until eventually you're, say, 50 meters beyond it, and the jointers have said, this cable is dry, it's good for jointing onto. You'll then test the cable and prove that that section of cable is good and it doesn't have any issues. And then you'll pull out of your new cable out of the carousel or off the reel and pull it down the deck and overlap it with the old cable. You'll then lift on your jointing habitat, and then you'll do your joint, which, as I say, could take up to 5 to 7 days. Once that joint has been done, you'll then do another test, and you'll prove that that joint is good before you then start deploying it down to the seabed. So you'll lift, once the testing's done, you'll lift off your habitat, and you'll start laying away. And what that means is you'll start laying cable, basically. And while you start laying cable, you'll lift and overboard the joint at the same time, which is what you can see here. And you'll lower that joint down until it's in the catenary, which is a section of cable coming down from the chute down to the seabed. And then you'll put the ROV in and you'll disconnect the crane off of the joint. You'll then continue to lay the cable, and that joint will slowly come down until it's resting on the seabed. And you'll continue to lay. You'll have analysis for all of this. So you'll be doing your lay in line with the analysis. So basically monitoring what the tensions are on your tensioner, and then also what the position of the cable is on the seabed, until eventually you get to the second end that you prepared earlier. You'll then put the ROV back down with a winch wire and or a crane, and you'll connect onto that end of the cable. You'll then recover that second end up to the vessel. However, what you've got to do is get that cable all the way around the cable spread, so along this port side, around the quadrant, and overlap it at your jointing location. So in order to get slack in the cable to be able to do that, you need to continue to lay more cable and pick up cable at the same time. So you'll pick it up, you'll lay away, and you'll pick up and you pull it all the way around until you're in a position to joint it. So you'll then, again, lift on your jointing habitat, do your joint, takes 5 to 7 days. And then once that's done, you'll test the cable again and you'll prove that that joint is good. Once that's done, you're ready for the final stage of the operations, and that's laying this bite of cable that you've got on deck onto the seabed. And in order to do that, you basically have got to get the vessel out from underneath the cable. So what you'll do is you will move the vessel forwards. So move the vessel forwards 1 meter, and at the same time, you'll pay out on the quadrant 1 meter. And basically what you're doing is you're sliding the quadrant, like on the rails, down the deck, and the vessel's coming out is moving forwards at the same time. Whilst you're doing that, you're also lifting and overboarding the joint, which you can see here. This will have all been engineered in so that the joint will be lifted and overboarded, and it'll land on the seabed when the quadrant reaches the chutes at the stern of the vessel. And the reason you want to do that is you don't want to overboard the quadrant with a joint that weighs 3.5 tons hanging on one side of it, because it creates like an unbalanced load. So basically you'll end up in a position where quadrant's on the seabed down here, and the joint's on the seabed down here, and the quadrant's at the chute here. And you will then connect the crane on and you'll lift and overboard the quadrant, and you'll hang it vertically, and the cable's then hanging in a loop off of it. You'll lower that down to the seabed while the vessel moves forwards, and eventually you'll get the quadrant and the cable in a bight on the seabed, and you'll trip the quadrant. And I'm just going to go through what that means in the next slide. And that allows the cable to be left on the seabed and the quadrant to be recovered. Once the cable's safely on the seabed, you'll then go back with your controlled flow excavator, bury the cable, and do your final handover testing of the cable. So if you get into cable installation, then you'll hear a lot about quadrant tripping. And so I thought it'd be quite good just to go through that. Basically, this is the quadrant where you'll have your loop of cable going around it. And in the middle of the arch, you'll have some rigging attached to it. And that's what you use to lower the quadrant down to the seabed. And that's what you can see down here. So the weight of the cable and all of the cable and the quadrant is hanging off of a winch and or the crane. And it's connected onto the top of, the middle of the arch here. You will also have rigging, which is slack from the top of the quadrant, so attached onto these rigging points, back to the winch or the crane as well. But that's slack at that time. And you'll lay the quadrant down on the seabed. And once it's all lying on the seabed, you'll disconnect the rigging from the middle of the arch here, and you'll then lift up on the rigging that's on the top of the quadrant, which is what you can kind of see here. And what that allows is the quadrant to tip up, and then it allows the cable to slip out of it, and then that's how it's left in a bight on the seabed, and then you're okay to recover the quadrant to deck. Sorry, I'm not sure if I've gone over there, but that's basically it. This is video, but I'm not sure if I've got time to play it, so I was just gonna. Also, it's got really loud music, which is like dance music, so it's kind of didn't want to blow everyone's ears off. How do I get my clicker back? Not sure if this is going to play.
Towards the bottom, but we should hover the cursor along the bottom of the image.
I'm doing it, but it doesn't seem to. Maybe if I do that. Maybe it's not going to. It's just a video of us doing a cable load in. So we're loading cable from a vessel into a basket, but it's actually the same process coming out. So I was just going to show that. But
you click to the next slide.
Oh, do I need to? No. Okay. Sorry, can't show it. But any questions on that? No. Overpressed.
Give you the mic.
You may have said it, but is there a depth limitation to this?
Not for subsea power cables. Are like kind of we were talking about yesterday. Is that they're relatively shallow,
Yeah.
so not necessarily. You would do it in any of the water depths for a repair.
Cool. But when we're considering future deep water wind, is it still going to be applicable?
Good question. I'm sure it'll be planned in, or you maybe end up having to do a full end-to-end replacement depending on what it is.
Right.
So just take the whole cable out and put it in. But the issue that you'll have is the weight and lowering that amount of weight down. So as long as that's been engineered into the quadrant, then I can't see why there wouldn't be, and you wouldn't be able to do it.
Okay, last question. From Steve.
Yeah, thanks. Actually, it's related to the question that's just gone. In the past, certainly we've discussed using airbags to get the cable up from deeper levels, but I haven't had that discussion for a while. I just wondered, is that still going on, or is?
I haven't heard of it.
No.
I think the issue you'd have is having it controlled enough that you might not lose, so you don't lose control of the cable.
Yeah.
Also, if you use airbags, if one of them punctures, and then you get maybe some sinking in the cable, and again losing control of it.
Yeah. We were talking about like elongated bag with 2 or 3 separate pouches, so to try and get around the problem you were talking about. No, I just wondered if it had gone any further, because we had a sort of a session on, well, how would we do a deep water repair, because people keep talking about Iceland, there's lots of power there, but you've got to get across that trench to get to Scotland. So no, it's good. Thank you.
Okay, thank you.
Thanks very much.
Okay. Next presentation is from Alistair Wilkie, HMO Chairman on Telecoms Cable Repair.
Good morning, everyone. I hope you all had a good evening last night, and I'd like to say thank you to ESCO, ICPC, Suboptic, and congratulations to all the award winners last night. My name's Alistair Wilkie. I'm chairman of the Atlantic Cable Repair and Maintenance Agreement. We currently run 3 ships in the Atlantic, one in the UK, one in Portland in Dorset, one in Brest in France, and one in Wilhelmshaven in Curaçao. We're a non-profit organisation, so we get money in from our members who pay for the maintenance of their cables, and all goes to the ships, and then any money left over at the end of the year just goes back to the members. So totally non-profit, except Clive is my secretary and I'm the chairman, and we have a contract management group chairman, Anders Teisdale from Tampnet. Clive and I are independent, and Anders works Tampnet, but that's just a fate that we've ended up in. We only repair cables. That's all we do. We do allow our members to use the ships for, I think it's on this slide, for small installations, particularly in the Caribbean, if you've got an island that you want to connect up to. So we will allow the maintenance ship to be used for that. Can't plow, unfortunately, because that's the way we have the ships, but it can do any other work. So it allows our members to have some cheaper alternatives to using the larger installation vessels, which are currently very busy doing other work. We have been in existence for, Clive, you can remind me, 50 years? Yeah. 50 something years. So founded really by AT&T, BT, Deutsche Telekom, France Telecom, who were the cable owners and the cable ship owners at the same time. And they've obviously divested most of the ships, so AT&T have moved their ships over to Subcom, but we've provide that service. We have 3 depots we have, Brest in France, one in Portland, Dorset, and one in Curaçao is actually run by Subcom, but we share it with the private maintenance agreement, which is Alcatel. These are our 3 ships and their base ports: Sovereign, owned by Global Marine in Portland, the Pierre de Fermat in Brest in France, and the Sentinel in Wilhelmshaven in Curaçao. If you imagine this place that we've got to look after the ships, it's quite a large area, and there's a map coming up. I'll show you where the area is, but it covers an awful lot of the Atlantic and the Eastern Pacific, all the way down to Terra del Fuego. So why do we still need ships? If you imagine, most of the cable owners now have a mesh network across the Atlantic or down to most of the places. There is a point where you might say you can get rid of ships, certainly on 24/7 standby. But the actual mechanics of it and the maintenance cost, it doesn't make much difference whether you've got a ship on standby available 24/7 or a ship on standby only available once a week or something. It doesn't make any difference to the cost of running the ship. So you might as well have the ship on 24/7 standby. We run them mainly to protect our cables. Damage is caused, as we all know, and I think Andy will give a nice presentation later on about this, but 86% of the damage is from third parties, mainly fishing, some anchors, and with the rest attributable to natural causes, 14%. In this part of the world, it's predominantly fishing and anchors. Where I've spent the last 10 years in the Caribbean, it's predominantly natural causes. It's earthquakes and volcanoes are our main issue. Interestingly, not hurricanes. Hurricanes damage the land-based network, not the sea-based network. But the volcano in St. Vincent took out 2 cables 30 kilometers away. And Mike has been doing quite a lot of research into that and the pyroclastic flow that went down and took the cables out. And the large earthquake off in 2011 that took out a lot of Port-au-Prince and Haiti also took the 2 cables out there as well. So even, as I said earlier, even though we've got these mesh networks, we still need to maintain the cables, and we still need this 24/7 capability. So starting back a little bit in maintenance, we look at the terrestrial side. We start with the cable landing station. So there's a different risk profile. And we also look at different risks for different types of cable landing stations. So you can imagine an international cable landing station that's connecting continents together has to have a much better protection than a small one on a Scottish island that just connects another Scottish island. So you'll have a different set of criteria and risk assessment to do on that. The main thing that we've found on the terrestrial and on the marine segment, the biggest issue we've got is having good records of what is where and where everything is. Particularly if you're buying distressed assets or you're putting new systems in, make sure you've got all the records of everything you've got very accurately. The amount of times we've come along to do a repair on a cable and we get told, oh, we think it's out there somewhere. Yeah, well, that doesn't help us. And then they work out it's actually on land. So make sure you know where your faults are. It's come out, the colors have come out all right. So this is a risk assessment we've done based on where the elements of the submarine cable network elements are and what the risks are for doing each one. I was at a defense conference with John earlier this week, mainly Navy people there, and they're all saying, well, the risk is high for submarine cables, et cetera, et cetera. And I got asked the question, so between a depth of 3,000, 6,000 meter deep, who is going to break your cable? Oh, nature. Nobody else is going to break it. You're not going to send a submarine down there to do it. You're not going to send anything down to break the cable. You're not going to find cables in that depth of water. So sometimes the defense people seem to have the wrong idea of what we're doing and what we're trying to protect. So that's John and I have got a little bit of work to do at the next conference, I think, to do some education at the Gothenburg conference. So that's just one thing we're looking at as well. I'll pass this slide over. It's to look at landing stations and the beach manhole, the three types, as I explained earlier. We've got three different types of risks that we've got in that one. I presume the slides are being sent out, Clive, to people at the end? No?
No, there'll be a link to the recording of this.
Okay, that's right. So people can see that afterwards. So again, back to the documentation. You need to have everything very well documented, where everything is, and have your initial baseline of your OTDR and your COTDR traces done. That allows you to work out where your faults are. So without this, you're really not going to get very far. And it's, as I said earlier, it's been a real issue in the past to get the documentation through to a lot of people. So where does ACMA look after it? So ACMA goes all the way down, as I say, we cover the maps. Slightly wrong. We actually go much further south. We go down all the way down to Terra del Fuego, and we actually go to repair in Terra del Fuego, starting fairly soon, I think. It's a cable called Fiber Optic Austral, and it connects Terra del Fuego up to Puerto William and Puerto Arenas in southern Chile. So they've got a fault, first fault they've had ever. So they're going all the way down there. These are the consortia-based maintenance agreements. ACMA, NAS and North America Zone in the northeastern United States. Sort of northwestern United States, Siokma in the Southeast Asia, Indian Ocean, and Yokohama zone covers Japan and around there. And then you've got the private agreements. So you've got Alcatel private agreement in the Atlantic, Siokma, South Africa, E-Marine, which cover Middle East, PEAT, which is the Pacific end-to-end, which is partly Alcatel, partly OMS, and the South Pacific zone, which is OMS in the South Pacific. IT International Telecom cover some of the Canadian islands as well. You'll notice, as in both maps, the previous one and this one, there is a big gap between basically southwest Chile and New Zealand. Now, there are no cables through that at the moment yet. There will be a cable Humboldt and possibly a cable from China to Chile and Ecuador. So there will be cables that. So that's a discussion that I'm having with others as to how we maintain that area of the sea with very few cables, but they'll still need maintenance. So as Matt said earlier in the previous slide was talk about depots and where you store your cable. This is a telecoms depot. This is Portland, owned by Global Marine. Very large. We don't worry about putting cables on carousels or on reels. We can coil them up. Twisting doesn't matter to telco cables. So we coil them up and they store many thousands of kilometers of cable in the depots. The one in Bermuda is slightly smaller, and one in Curacao is a similar size to this actually. So we look after them. There's air-conditioned buildings. Make sure that you don't want sunlight on the cable because it damages the outer part of the cable. But in the outer ones that we have in Bermuda, we just put tarpaulins over the tanks. All the amplifiers are kept in here, and they're kept in good storage spaces. So going through the maintenance, it's almost identical to the power cables, except our cables are smaller and we do it in deeper water. How do we do it, and why do we do it? We have two fault types. We have shunt faults and we have full breaks. So this is a shunt fault. Top right picture is actually caused by abrasion. It was strumming over another cable. The other cable had a harder outer, so it eventually strummed down. We ended up exposing the steel wires, and the copper got worn out, and we had a shunt fault. The bottom left-hand one is a blowout, actually again caused by abrasion. This was taken from the south of the Grand Banks, where the Labrador Current strummed the cable over very rough seabed, and eventually just blew the cable out, and the cable blew out completely. Took the fibers with it, and very easy to find the fault on that one. That was in about 4,000 meters of water depth. So the top right-hand one and the bottom right-hand one are shunt faults, and the fibers are still intact. Deep water long haul cables with COTDR, you've got an idea where the fault is. You might be plus or minus 100 meters or 200 meters. That's close enough for the cable shipping, that depth of water. Shallow water faults, we need to be much more accurate. And that's where we find the OTDR is better, and you try and blow the fault out to break the fibers to then find the fault better. Fault detection, as I said, OTDR on the shore ends. Shallow water is the easiest thing to do in the unrepeated systems. COTDR does a similar thing. It's not quite as accurate unless you've got a lot of time. One of the issues we're going to have going forward is the 24 fiber pair systems that Meta and Google are putting in across the Atlantic. Doing tests and COTDR, they're currently about $300,000 each. You're not going to have 24 of them at either end. You're going to have one. So testing the fault is very, very slow during repairs. So that's one of the issues we have. A pure shunt fault, Rob Strugino will talk about shunt faults a little bit more after this, but pure shunt fault is actually quite complex to find. If there's just an electrical fault, the cable, whilst the old analog cables had known and set impedance and resistance, we calculated very accurately. The newer optical cables, we're not interested in that. We're interested in fiber. So getting the fault is quite difficult. So that's why sometimes blowing the fault out, putting a higher current through, trying to blow the fault to break the fiber to get the position is better when you've still got to do the repair. Fault finding in very shallow water is quite easy. You use that as a diver's probe that we can use. We can go on the beach. In semi-shallow water down to a few hundred meters, even 1,000 meters deep, we'll use an ROV with electroding tone or a pipe tracker, TSS pipe trackers. And then in deeper water, you know roughly between which two amplifiers your cable is broken. So we just throw a hook over the side and drag it across the seabed, and it works. Grapnel types, on the left are Rennies. Giffords and Rennies are very similar, but those are Rennies. We use them in deep water. And the one in the top right in the middle there is a long prong cutting flatfish, which we drag along the seabed, and that will cut the cable. And then we can use a long prong holding flatfish. So you just put a holding piece in instead, you take the cutting blade out, put a holding piece in, and we use that to fit the cable up afterwards. These are from one of the subcom ships. I was doing a repair some years ago, and they're nice and clean and new. When they've been dragged across the seabed, they're looking a little bit rustier than that. So this nicely painted. So this slide you'll have seen last year. It's from Paul Stalley, who did this presentation last year. This is the process. Matt did a wonderful presentation about the process on the power cable. It's very similar on the telco. It's just that the cable's smaller, lighter, and we don't have to worry about quadrants and cranes, etc. But the process is easier. We don't need to move the habitat to the cable. We move the cable to the jointing space, so we can move the cable around much more. And we move it quite quickly. We locate with the ROV or the electroding, cut, pick up the other end, go to we take buoy one end off because it's the easiest way to do it, especially in deep water because you don't want to do the grapnel runs again. Cover the second end, remove the damage, test the cable back to the cable station, joint in the replacement. Joints, our joints in deep water take about 14 hours. In shallow water will take about 24 hours, depending on how many armor wires you've got to put on. You lay the replacement cable in, do the final splice, as we call it, test from both ends. And this is where the testing from both ends is getting the problem now. As I said, 24 fiber pair deep water, it could take about 8 hours to do the test if you're lucky. The other problem we've got are the shallow water cables, the cables across the channel now, 192 fibers. Are we going to test all 192 fibers? Are we going to let somebody sit with the OTDR and just go one after another, which could take hours, or we're just going to do some random testing and hope for the best? So At the moment, they're just doing random. They're just doing testing one or two fibers per tube and hoping that the rest of the fibers are okay. The splicing systems are so good now that they're pretty accurate, and you'll see on the splice whether there's any real issue with the joint. We then lay the final splice. In deep water, we lay the bite out, and we use a hook that we can send a pinger down to, and that a bite release hook, and that releases the cable probably a few hundred meters north above the seabed, and we just let the cable drop onto the seabed. There's no quadrants or anything to put the cable carefully down. We don't need to in deep water. Shallow water, we'll lay the bite out, and then we use an ROV to go around and inspect it and rebury it. Talking about the joints, they're quite small, about a meter and a bit in length, and add the buffers on, it might be about 2.5, 3 meters in length in total. And two people can easily pick them up, and they're about 50 to 60 kilos each. You have, starting from the late 80s, again, it was the same companies, it was AT&T, BT, France Telecom, and KDD in Japan, decided that they were struggling to have 4 sets of jointing equipment, 1 set per manufacturer on the ships. So they got together and designed the universal joint. So you've got a common component kit in the middle, and end-specific kits for each manufacturer, and then you've got the outer protection. That has meant that we have 1 type of jointing equipment per vessel, and 1 set of training to do, and we can joint almost any cable to any other cable. Now, the power cable industry should learn from this, I hope. It would be nice if they could have, certainly on the smaller cables, the 66 kV, maybe the 132 kV ones, if there was some form of universal joint. Whether the manufacturers of the power cable are willing to go down that route, we don't know yet, but it has been talked about. But the universal joint has been a revelation, really, and helped us get going and doing the jointing very quickly on the ships. So if there's any questions, short and sweet presentation. I would like to add that after seeing the awards last night, the ACMA we're doing an award for next year, and the prize will be attendance at our 2 annual meetings. So we have 2 meetings a year. One is the contract management group meeting, which is commonly in somewhere warmer at this time of year. Clive and I are going off to the Caribbean tomorrow. So it'll be somewhere in the Caribbean or round about there. And the second meeting will be normally somewhere in Europe in the summer. So we try and stay warm most of the time. So that's for the prize that will be given out by the ACMA the next award ceremony. So there'll be for excellence in maintenance, and somebody's doing something in maintenance and someone in cable maintenance, either power or fiber optical. We don't really mind. So any questions can come to me. I'll be here all day. Thank you.
Yeah. Any questions for Alistair?
Is there a separation for fiber optics in deep water? So so you can do your grapnel runs and not pick up 2 cables?
So 3 times water depth.
Oh, okay.
Is the common number we would use, but you'd normally try and be more than that. You don't want to be that close. 9 kilometers apart allows you to grab for the cable, but in 3 kilometers of water, you'd rather be twice that distance apart. So yeah, but yes, the answer is yes. Yeah.
What do you find as being on the side of repairs? What do you find the biggest root engineering mistake people make with laying fiber optic cables?
The main mistakes that have been made in the past, less so now, cables are getting installed much better, is not taking into account the slopes. So you're laying across the slope, so turbidity, currents, and other issues, slope, take the cables out. Sometimes you've got no choice, and the cable that I've mentioned that Mike's been looking at off St. Vincent, we had no choice. You're going between St. Vincent and St. Lucia. There's nowhere else to go. So you run the cable through the gap, and unfortunately the volcano just moved the seabed so far that it took both cables out. But yeah, it's normally that. Currently, and the number of faults has come down significantly in this part of the world, mainly because we're much better at installing cables. They've worked out through sound waves, and particularly off Holland and Belgium, the sound waves. If you use a mass flow excavator now, you can basically get rid of the sound wave and you plow to the bottom of the sound wave rather than just plowing through And as the sound waves moved, cable will be buried one day and not buried the next. So that's been better. So it's mainly the better engineering of the cables, not really a risk.
Thank you.
One more question, anyone? We got any on the Slido, Ali? Okay.
With the growth of new operators, is this the right one? Yeah, sorry. With the growth of new operators laying cables, are there challenges to the repair model with these operators less willing to commit finance to repair arrangements?
It's an interesting question. Actually, what's now happening is that the newer operators are willing to commit to longer term contracts for maintenance to allow the maintenance operators to build new ships. The issue, if you keep giving a 3-year contract to somebody, they're not going to get enough time to buy a new ship at, let's say, 100 million, and then get the money back if they're only getting a 3-year contract. They're give them a 10-year contract, they can build the ship and get the money back. So the banks are willing to lend the money. So actually, they are coming in with money and saying, yes, we're willing to give you long-term contracts, which is good.
Time for one more.
One.
Yeah, sure.
What are your thoughts on using modular equipment instead of dedicated vessels for submarine cable repairs?
It's been used in the past. I think modular equipment has a place, particularly if you're doing repairs in difficult areas. So there are, Anitel in Brazil installed some cables up the Amazon. We don't think they're going to get repaired very often. A main cable ship can only go so far up the Amazon before we bottom out. So modular repair spreads up there. I've recently installed cables off Guyana and Suriname where you've got 40 odd kilometer shore ends. It's incredibly shallow. Again, modular is quite good there. The main cable layers now and the main cable maintenance ships, it's better to have them on 24/7 standby available. So modular doesn't work in that situation. But thank you for the questions.
Okay, thank you, Alistair. Okay, next presentation is from Bob Shugina on deep water operations.
There we go, see what happens. Oops. Okay. Okay, thank you. Right. Slightly different now. I'm going to deal with deep water. Deep water repairs are actually incredibly rare. You'll see from the fault statistics, it's somebody, I think it's 14%. Actually, that's gone up as a proportion compared to 50 years ago because burial and shorter stuff, shallow water, it's got so much better. And you've seen examples today, particularly from Matt there. I thought it was brilliant. Right, so now the quality of shallow stuff is amazing. Right, but I'm going to deal with long. Now, they don't happen often, and I'm here mainly because of my age. I've been doing them for 40 years, at least 40 years. And so I've seen more than most people and I've been involved in more. So that's the only reason I'm here, really. Now, you'll notice I doesn't say on there, but I'm a mechanical engineer, chartered engineer, and you'll have seen that the amount of engineering that's required these days, particularly in the shallow water areas, is immense. And so you can see why the power of engineering, if you like, it's the wrong word, but the influence of engineering is greater than it used to be as well. Now, being an engineer, the bit I'd like to get across, if you can, is that engineering is all about teamwork. It's all about teamwork. It's not like the financial sector. It's no I ams, it's we. So if I say I, please forgive me, I'm just an old man, I forget the stuff. But the reality is, I have never achieved anything on my own. I've always relied on a massive team. And if you can create a good cooperative team, and you get the atmosphere here a little bit last night, right, it goes so much easier, believe me, right? So I'd like to do that. And the other thing that happens if you're an engineer, you stand on the shoulders of the previous engineers, right? And the three I'd like to mention today are Zajac, Roden, and Richardson of Bell Labs. You'll never hear about them again, but to me, they're my heroes. And I'll come to them in a minute, right? Now, just to show the bit I'm talking about is, this is a typical fiber system. The cable station or a route position, whatever they call it now, a data center. Cable goes down, it's usually buried in the shallow water down to about 2,000 meters. And then we get into the deep water, 2,000 meters and beyond. And that's all I'm going to talk about. You've heard a lot about this. This is where 90% of the activity is. This is the bit that nobody hears about because hardly anybody does it. And it's surprisingly different. And I'll hope to show you why later. So just to clear, the only sort of cables I'm talking about, Andy handed one out yesterday. I'll hand this round. This is a lightweight cable. It's a fairly modern generation. You'll see it's got a core of steel. These steel, they're the strength of it. They're also in a circle, which creates a compression resisting medium in the middle. So in the middle, it's actually atmospheric pressure, believe it or not. It's almost unbelievable to believe that. And you'll also notice a copper, and that copper, go back to the first slide, you saw there with amplifiers, you need the copper to provide electricity to boost the amplifiers. So that's power. Now you'll also notice there's no return, right? So what we do is we apply the voltage from either end, usually plus at one end and minus at the other, and we use the earth. And there's talking about niches, there's people who specialize in making earths at the earths, as it were, and they need to be right, otherwise it doesn't work. Right. So there's a niche everywhere. It depends who you are. So that's a typical. Do you want to press it? I'll put it here. And this is a slightly earlier generation. Still a lightweight cable, but it's got an extra jacket on the end, and I'll explain why in a minute. And the reason for the extra jacket is we've talked about the abysmal plain and how it's all made of basically millions and millions or trillions, billions of years of fish debris and stuff like that. So if you think about it, it's mostly flat and it's really soft. On board, we used to go out, we call it Atlantic mousse. You know, it's a bit like Angel Delight. Do you remember Angel Delight? It's like that, right? We used to play games and put it in people's dinner, colour it pink, put a cherry on it. Really antisocial behaviour as you get on ships. Right? No, but it's not always like that. This is a cable running from UK to America, and it goes through. These are sea mounts off Newfoundland from memory, and you can see it's actually quite tricky there. You can't go over the mounts; they're really steep. So they're dead volcanoes. They're everywhere, right? But no, not everywhere. There are in places, and sometimes you cannot avoid them. So what you do, you try to go through them, right? And that's where that black cable is very useful. If you're really interested, I've got a sample from down there, came up on the grapnel. I used to be a devil on the ships. If I saw something, right. And I've got, if you want to touch that, I've got it. Right. So you can touch the bottom of the Atlantic today. So that's the two different cables. Now, I'll now go to Zajac. I go back to the days before computers and all that stuff. So we had to do it using our heads. Now, nobody actually really, until differential calculus came along, and that we didn't really have a way of doing it. The man who solved the problem was a man called Zajac. And he, the unbelievable thing, this is only for telecoms cables, definitely not for you, anybody else, is that as the cable, let me get the piece back, as the cable sinks through the water, it's pushing away through the water. If you think there's drag that way, right? And what you want to do, you want the cable to conform to the seabed, and the only way to ensure that is the touchdown temperature. Touchdown tension has to be 0. And that's what you. Now the maths of it all. If you go through the maths, and I will encourage you to do that. The maths of it all is summarised in their book. And this one's by Roden and Richardson. They followed on, but it's all based on Zajac. And now Andy last year managed to post it to everybody if you want to read it. It's all in old passion units, if you like. So it's a nightmare. But what they've got in here is the thought processes, and all that now is encapsulated in these computer lay programs you'll have, Mackay and all those people, right? So they've taken this and they've basically computerized it. Now, the beauty of that is if you run it without computers, and I have run it without data logging machines, you don't want to do that. But if it's in a data logging, it's so much easier. The downside of it is the understanding of what's going on outside is lost. And I'll be honest with you, I've made a bit of a living out of dealing with the fact that they've relied on the computer. They've looked at the computer's saying it's all okay, and it's not. And I'll explain. I can only give one example, but I'll do it. So Richard's my heroes by a long way. Now, the main point is the answer is a straight line when you're laying in deep water. Now, what happens is the angle, this stuff is really quite light. It sinks quite slowly. Now, if you think about it, and if you're going at, say, 7 knots, which is quite not untypical, the angle of departure from the ship can be as low as 7 degrees. 7 degrees. Now, any math, I wish you were all Hannah Fry's, right? Because she'd be on this straight away. She'd work out the layback distance. How far behind it is it, right? Now, the problem isn't so much, it's actually tens of kilometers, right? Tens of kilometers. It can be up to 40 kilometers. That's a long way. So the touchdown point is not, 50 meters, 100 meters behind you. It's over the horizon. So when you're on the ship, your brain needs to be back there. On the ship, but back there, right? And the problem is, I hope it's showing there, some of the seabed contours are shallower than 6 degrees. A lot steeper, sorry, than 6 degrees. The cable is shallower. Okay. Now, this is typical seabed, transatlantic seabed for TAT 8. And you can see it goes up and down. There's a couple of seamounts. And the problem is with this is you have to survey and know what the angles are. No, we all do it from the surface of the ship because it's cheap. Now, they're using sonar. So the pixel size, by the time it's down there, is actually huge. And I will admit something now. It wasn't TAT 8. It was on another one. I won't tell you which one. We did it. And all I can say is that I had a phone call from David Mearns. Now, David Mearns is a deep sea hunter of wrecks. And he found the Bismarck, and he said, Rob, you do realise you've laid your cable through the debris field of the Bismarck. What? How did we miss the Bismarck? It just shows you at the resolution down below. It's possible to miss a ship the size of Bismarck. Just think about that, right, for a minute. Now, the other thing, you now know that the angles on the seabed are greater, steeper than your lay angle. Now, what's to stop you going over the speed? You can lay at any speed. You could lay at 10, 20 knots if you wanted. What's to stop you? There isn't anything to stop you, if you think about it, right? And so this Zajac man, or Roden, one of the two of them, decided unbelievably, he sat down and worked out what happens to the cable if you don't slow down. That's really good people thinking, right? And this is what happens. This is for the Mid-Atlantic Ridge. It's a cable not dissimilar to this one. And you'll find that the faster you go, so you want to go at 6 knots because you're all under compression. You guys, you're the cable owners. You put so much pressure on the ships to go fast. You want the lowest price. All they care about, right? And the only way the ships can do that is to go faster. If they go fast over the Mid-Atlantic Ridge, you can up to 30% of your cable will be in suspension. Is that a good idea? Is that a good idea? Has any of you been in the Atlantic? Has any of you tried to pick up anything in the Atlantic? I'll tell you one thing. I've seen buoys the size of this room, all the correct weights on them sink because the what do you call that? The Gulf Stream. In some places, it's an awful lot more than you thought. And that's just the surface. So you're the guys that control it. If you're their project manager or offshore super or just anybody really involved in the route planning and all that, when you go and select your contractor, your marine lay contractor, make sure, ask them, could you see their lay plan? Could you see the time they've allowed for it? And if you haven't got this slowdown in the plan, you want to start asking questions. Who is doing this? And the other thing you want to do, make sure, is that everybody, the captain and every watch leader who's on duty knows this, right? It's so easy for them to put the pressure, we're behind, there's a bit of weather coming. If you do that, you're taking a risk. So it's up to you guys. And you need the confidence to ask those questions. If you want the confidence, read that. Right, now I'll give you an example. This is I love this area. This is the Japanese trench. I absolutely love this area. But it's a challenge, and it's a subduction zone. You've all watched a TV. Subduction zones, they go down like that, and the other one comes on top. Right, that's it. That's in your head, right? Correct. It's not like that at all. It's like this. No, this is obviously stretch, but you'll see. It's different sizes, but there's an upside and a downside. But when down here, it's not like that. This is I forget how long this is. It's something like 50 kilometers. It's flat. How can it be flat? Right. Now it's at 9,000 meters. This is 9,200 meters. I thought the machine's not working. We all rely on those machines, the pingers. No, it's rated for 10,000 meters. Anybody tested it? 10,000 meters? There's nobody to test it. Oh my God, it's the machine. It can't be like this. It is like that. Right? We did it twice, did it 3 times. We did Google Maps and all the stuff. It is flat. And what it is, if you think about it, it's all the detritus sliding down there and it fills up the bottom. Well, it's obvious when you think about it. But when you hit it for the first time, it's not obvious. But you'll also notice this. Right? It's going up and down. Oh, hang on a minute. You've got to remember that when you're over here, up here on the ship. How are you going to fill that? How are you going to do it? That's why you need all that computer stuff, right? But there's a complication. And Alistair's alluded to this earlier. These currents, the Gulf Stream, this is the Caruso current, the East Africa coastal current, I think it's called. They're all over the place. My first one was the Med. Going across the front of the Med. Oh, God. And what it is, it's all been caused in the end by the ship being told to do it at this speed and it's too fast. They haven't allowed enough for the cable to conform. Right. So, and that's because the commercial pressure that's all it is. But, and so when you go on board the ship, you go up to the captain and when you've done, oh, yeah, I'll tell you what, the biggest surprise, you have to slow down and you have to do it so early. And that's because it's 40 kilometers behind you. Hope that makes sense. And Alistair saw some of this. This is what starts to happen. If it's strumming, and you don't know, there's no way of knowing that. You could send a submersible down and check it beforehand, but it changes from day to day. And what happens? You start to get this. Now, what causes that? Well, this particular one, I've got a sample of. I haven't got it from here, but if you go to Cornwall, you get that shale. It's so thin, and you fall it always cuts you. It's that, and it just sits there and it's strumming away. And what you can do, done this. I say I'm true. I Japanese ship, fantastic people to work with. I asked the crew, would they mind? We inspect every section as it came in, and that's what we're looking for. And then we could get the wavelength of the suspension. If you think about it, the points where it's touching, you get the wavelength. You can almost work out how fast the ship went from that. That's how I know these things. Right? I'm there with my magnifying glass. And there, as Alistair showed, it gets deeper and deeper, right? And eventually you get, and Alistair, I noticed this was used yesterday by, on the, not Alistair. Anyway, they had it, the Shy was there yesterday. And what's happened here, this is a cable. Now, unbelievably, this was still working. We had a particular problem with this. It's a cable where it comes across the Pacific. The beauty, and I love this cable. The reason I like this cable is, and it becomes clear later, it's not where the others are. There's only one place in the Japanese trench you can cross and keep within the depth requirement of cables. They're all classified, qualified to 8,000 meters. So there's only one place, and all the cables go through it. Now, I've been there, I've worked on it, I've seen cables tracked there, it's a nightmare. But the people that own this, and this is where I like this industry, you come across really brilliant people. And somebody said, well, the only way around this, we got to go deeper. So, discussion with the owners, cable manufacturers. Well, actually, it's just not reusable. You can actually put it down there and it will survive. So they took it hundreds of kilometers further south. They got it away from up there. But within a year, now it started to, how it fails, you get a shunt fault. Now, you can actually run a cable optical system with a shunt fault. And what you do, it's 10,000 volts, and normally you put 5,000, plus 5,000, minus 5,000. But if you get a fault which is not in the middle, right, a shunt fault, what you can do, you can trick it. You can raise, you make the voltages plus and minus in proportion to the distance to the fault. And it's possible to get like a virtual earth at the fault. It's not a virtual earth, it's a real earth, right? And what it means is you can power the system up. It overrides all the safety features because it thinks it's intact. And you can do this, right? But once you start doing that, you haven't got long because you can never get it perfect. There's a little bit of leakage of current, a tiny amount, but corrosion occurs. So that steel in the middle, the corrosion, it starts eating away. And there comes a moment, and Alistair said they use this, they can use the imbalance to force a failure. They can cook it and corrode it fast. Well, we're doing the opposite here. We're buying time to prepare for a repair. So it's really, really good. And what I like about this, I took the ship, I asked the ship, but nobody knew what to do. It's so deep, right? And that's, I love those things. So I asked the ship, we've had too long. The fault position was moving. I said, we need to go January. As soon as we got the gear, nobody wanted to go. All these cases, we don't go in the middle of the Pacific in the middle of winter. It's front doors open. It's near suicide, right? No. This lab here, not this place, the data's in that library. I could go down there, study all the wave statistics for that area, going back hundreds of years. And from that, I could work out, and I convinced the ship they do trust me actually, it's a really lovely relation. I could convince them that there were the weather windows were just long enough for us to get from one bit, to get to a key bit where we could put the cable down. I could tell you a story about my religious experience, but I haven't got time. But it's amazing. And 85% of the cable strength was missing. But we were 20 miles away. We just give it a tiny little tug, and it broke. Amazing. But so it shows the resilience, the toughness of these cables. Amazing. So I've already said all that. I don't need to say that anymore. Now, one thing about deep water recovery is slightly different. During laying, the water is supporting it. When you're bringing it back up, it's cheese cutting through. It's a completely different ballgame, right? So during the hydrodynamic forces are now working against you, and a small change in you want it as vertical as possible. A small change in that angle, and I tell you what, as human beings, we're absolute rubbish at judging angles. Right, I'll show you what happens if you get it to do. And now I've done it as close as I can for one of these cables. Again, this is Zajac. Brilliant, man. And you can see now, these are for different recovery angles. They're quite small, 50 degrees, 60, and so on. Right? No, sorry. These are the different ones. 90, 85, 75. Right? And this is the tension going up depending on the recovery speed. And what you can see from that is, I'm going to say the permitted cable load is 50 kilonewtons and the braking load is 70 kilonewtons. If you're here last night or yesterday, I'll have told you the margin for error is remarkably small, right? And you can see how easily we use it up. If they get the angle of angular, the recovery angle wrong, very quickly, you're allowed 50, very, very quickly. That's only from 90 degrees to 85 degrees, 5-degree change, you've almost lost your margin, right? Really bad. Now, what you can see too, if you try to go fast, we're in 9,000 meters of water, right, round down there. Look at the recovery rate, 1 knot. 1 knot is 0.5 of meters per second from memory. So you can see, hang on a minute, 0.5. Just work the hours out. It's not days, it's not minutes, it's days. So you're going out, and you've heard about how quickly they can repair a cable out in the, out there on the channel. Sovereign goes out there, can get there, it's all mobilized, and you're back indoors, and you can be back home in 4 days. All done. Out there, 4 days. You may have just got the first end on board. It's a completely different ball game. And this is the hardest bit to tell. The only variable you've got, apart from, you have to get this vertical, the only variable you've got is the speed of recovery. And the only safety margin you've got is to go slower. So, I'll do this quickly. You can see the recovery is very low. Just to lift the grapnel with a cable on it can take over 16 hours. I've seen it take a lot longer. It's awful. And the pressure from the shore, please get on with it. We're doing our best, right? And so I say that, if you're in charge, please be patient with the ship. Nobody wants to be there. We want to get home. Now, and also remember, when you get hold of it, this is a grapnel, deep sea grapnel. This is a gripping grapnel. And what we particularly, I like this grapnel. It's Japanese, it's really good. And what happens, you can see it bends and it just grabs the center core. But in doing that, it damages it a bit. So don't forget, at this critical moment, as you're bringing all that high load in, you've got a weak point. Worse than that, you've got to get that off. How do you get it off? You bring it in, and somebody has to go down there and wrap a stopper on it. That's a way of getting a attachment rope onto the outside. Very dangerous moment. These are the ones where you just pray for weather. Right. So that gives you an idea. That's sort of long line, deep water bits. Now, some of the issues you get coming into them, which you don't get around here, hopefully, is long line fishing. Now, long line fishing is pretty unregulated, and everybody does this. What's the threats? And there it is. I think these are all wrong. Right. We're working over here. What do we run into? Long lines. Right. They're supposed to put their AIS on, but I think often they turn them off. So long lines, and what is a long line? I'll show you. Well, when you're on the ship, this is if you're lucky, this is what you see. This is in Japanese waters, by the way. So here you can see that it's pretty well marked. And in daylight, you can see it. Now it can be up to 50 kilometers long. It's a tiny well, I've got it here. It's a nylon rope, and these are hanging down off of it. Do you want me to pass this round? You've got to be careful. I promise you don't kill yourselves on it. Right? I'll leave it there. That's what you see, right? If you're lucky, you try and call the ship, the fishing vessel. Sometimes they answer, sometimes they're over the horizon. They don't hear you, but you can't continue. So, and this is what it looks like. You see, we've put a little hook on it, and we're pulling it up to the ship to clear it, so we can go through. But you see what it's pretty horrible. I call it 50 kilometers of death, basically, because that's what it is. Sorry for the environmentalists. Now, if you're not lucky and you haven't seen it, or it's on the cable already, and this is what's happening here, you can see the hook, perfect size, absolutely perfect for catching on our cables. Couldn't have been better made, could it? If you're lucky, you see it. If you have even more luck, yes, it's a turtle. It's in the middle of the Atlantic, and this curtain of death has come up with a turtle on it. What did we do? Now, this is where we turn the radio off. We turn the daily record off. We agree, as a ship, and Chris Packham will be proud of us, we decide to launch a rescue operation. That little fella, we don't know how long he's been there, but we do know he saved our cable, and we want to reuse this cable. So we decide, and you can see there, you can see we launch a boat, our only Z boat. This is so dangerous, really. And we get out there and we bring him back. We have to bring him back to the ship because we need dentistry, right? We need all the equipment to get that flipping thing out of him. And then later, when we've got him out, it's a Canadian ship, by the way. It's really eco-friendly guys. And we're now off the record, right? We're being controlled by a big corporation that would tell us to eat it or something. So we cut that, take it off, and then we say, take it away. I've got a video of this. And the bosun said, go away, take him a quarter of a mile. We don't want him in the prop. Fantastic. And that's a bit of life, which you would never hear of anyone else, I suppose. Now, if you're less lucky, oh dear, comes up like that. This is a bit of a problem. We want to reuse that, but this is what it does. If it slipped, if it hasn't caught, it slipped on the way out, or it slipped on the way up, you've then got this. I'll pass this round. So now we've planned to relay that. The cable ran from London to New York, and we want to divert it from halfway in the middle of the Atlantic, pick it up, re-engineer it, and lay it to Bermuda. Right? It's a good way of recycling. There's the recycling plan. That's bad news, isn't it? This is, I'll pass it round if anybody wants to see it. Bit of a headache. Even more of a headache is how do you do it? How did it happen? How did it get there? Right? How can you prevent it? Well, what I did, we had to reuse the cable. It's coming in mile after mile. What do you do? Well, what you realise, of course, is as you're picking it up, you're just making it worse. So unfortunately, the only answer is to let it go. So then you've got to go and start somewhere else. How do you know where to start? These are serious. This is where the lay data and everything is actually quite good. They're really good the marine contractors are normally really good, and they keep good records. You can relive every watch if you read the data and you know how to read it. So that's what I'm there to do. That's why I'm on board, right? And so what you can do is think, well, how would you prevent it in the first place? Well, to prevent it happening in the first place, it's probably happened at night. Well, it did happen at night. When they were laying it, they ran over a line. They didn't see it. And they caught the line round it, dragged it down and all the rest of it. But that's not in anybody's interest, really. The long lines have at the far end, 50 miles from the ship, or 50 kilometers, they have a buoy with a radio on it. So if the line breaks or gets cut, the ship doesn't lose the catcher or anything, really. All they do is they pick up the bit they've got hold of and run around to the radio bit, pick that up. They get a recovery. There's no loss, basically, just time. So what you can do is on a cable ship at the bow, put one of these over. So at night, well, all the time, really, for safety, because you don't always see them. Put one of these long line cutters out. And they're made in Southampton. So I'm a bit of a plug for Southampton here. And you can get them here. And they are worth deploying. And that's how I found it. I looked through all the day logs and I noticed when they picked it up to clean it up, at the change, it must change the watch. Often things happen, it changes a watch. The new guy coming on forgot to deploy it. And that told me immediately where it was safe to go to. Now, from this, you'll also realise that I've talked about it being teamwork. I've used the word I too much. It's not like that at all. And it's all about teamwork. And this is one of my favourite teams. And they treat me as an equal there. It's really, really lovely. And we've done some absolutely record-breaking stuff, the deepest deployment of branching units, deepest repair, all sorts of stuff like that. And but it couldn't be done. These are the world's best deep water men, in my view. And I've worked with all of them, really. These, if you want it in the Japanese trench, they know it like the back of their hands. Brilliant, brilliant. Now, I got into this game by accident, as we all do. I've always been keen on. I got involved in wind. I had to understand. We had a tower, one of these towers that you get. It was moving. The riggers wouldn't go up it, and it was too scary. And I had to work out what that was all caused by. And I realised there was energy in the wind at different frequencies. And today we call it gust spectral density. We didn't have a word for it in those days. But when I went to see, I thought, oh, it's the same here, but it's in waves. So we now have wave spectral densities, right? Now, we all know, these guys know it like the back of their hands, right? They select their ships based on their response amplitude operators and the spectral density. It's all the maths. Said we need Hannah Fry here, really. But it's really, really good to know that stuff, because you make sure then that the ship, if you ask the right questions, you can make sure the ship matches the environment it's going to meet. And it gives you the operational envelope for that ship, right? But we all know that. Well, yeah, the marine people do, right? But in there, one of the characteristics of it is, I'll try and get this right. Every 36, statistically, could happen in a minute. Every 36 hours, the highest wave will be twice as high as the average of the third highest waves in 36 hours. Terrible concept, but basically what it means is every now and again you get a rogue wave, basically. No, I've been doing this for years. This is the middle of the Atlantic. We're doing a recovery. You can see the cable there. There's a man sitting there, exposed to it all routine, pretty flat. That's what the maths mean. Any questions?
Thank you, Rob. Again, a fantastic presentation. We haven't got long for questions. Is there one or two for Rob?
During either repairs or installation, do rogue waves cause problems if they're unexpected?
No, they don't really. The Derbyshire's in my mind, right? And I've been on a ship when, for various reasons, we lost power, and I've been broadside on in a hurricane. And the ship stability runs out at 40 degrees and it rolls over. I've been to 39 degrees, but I'm still here, right? We've not lost a ship, a cable ship. They're very vulnerable ships, and because they're vulnerable, and they're vulnerable for a reason. If you think about it, a ship's stability comes from the cargo in it. But we lay our cargo at sea. We're the only ships really that go out fully loaded and come back empty. So it is quite. You have to have people on the ship who really take that seriously, because otherwise the ship will roll over. And we've got the front door open. If we get that wave come in and into the tanks, it's a free surface effect. Freedom of free enterprise over on its side. So everybody that's involved in this game knows it's dangerous, right? And so we keep within the operational limit. That's what we do.
Thanks, Rob. Thanks again. Okay, over to Harriet to give an overview of those great presentations.
Some fantastic presentations just there. Honestly, I was kind of still giggling about the man that's on the boat being absolutely demolished by the wave. So we've just had a focused look at what happens after a subsea cable is damaged, how faults are located, how repairs are executed, and what it takes to restore these services as best as we can. I think the key point to take away here is simple. Repair capability is a core part of system performance. You know, this is not a secondary consideration for these systems. The ability to respond quickly and effectively to a fault is just as important as how the cable was originally designed and also installed. We also heard how power and telecoms repairs share many common steps, but I think they also differ in many important ways, as we heard. Both require rapid fault location, mobilization of specialized vessels, careful recovery of the damaged section, jointing of replacement cable, and reinstallation with appropriate protection, all within our congested seabed with our busy cable corridors, as Matt pointed out. However, cable repairs are often involving heavier cable, higher voltages, lots more money, stricter safety controls, and more complex testing before the system can be returned to service. On the other hand, telecoms repairs may involve different jointing techniques, repeaters or branching units, and can place a strong emphasis on restoring traffic as quickly as we possibly can. Another strong message was the impact of water depth on repair strategy. So as water depth increases, operations become more dependent on remotely operated vehicles, specialist handling systems, and precise vessel positioning. Things like weather windows, vessel availability, and equipment reliability all become even more critical at this point. Deep water repairs are feasible, but as we heard, they require a higher level of planning, of engineering, and contingency preparation. The presentations also reinforce the importance of being fully prepared. This includes having fault response plans, framework agreements with repair providers, just as Alistair described, access to spare cables and joints, and up-to-date route and asset information. Projects that invest in being prepared can move quickly from fault detection to repair, significantly reducing outage and duration within the overall impact. Another key takeaway is the close link between design, installation, and future repairability. So what can we take away overall? Decisions made during route selection, burial depth, protection methods, and landing design directly influence how easy or difficult a repair will be years later. Designing with repair in mind is therefore an essential part of building resilient cable systems. To conclude, what these presentations collectively demonstrate is that effective repair capability depends on planning for faults from day one, having a resilient team, as Rob mentioned, recognizing the added complexity of deep water, maintaining a high level of planning and being prepared for these situations, and designing cables with future repair in mind. So just to remember that no matter how well installed and buried, as we heard in the presentations, there are always going to be damaged cables, whether that's by nature or third parties, but minimizing these risks as much as we can is the crucial final step of any planning system. So thank you very much, guys. I'll hand back over to Clyde.
Thanks, Harriet.
We are running a little bit late, so Q&A may need to be a bit restricted for the rest of the day. But the next presentation is on protecting cables from damage, and as part of that is global repair commencement time analysis from Andy Palmer-Felgate.
Move the slides on.
Yeah. There we go. Okay, good morning. Not sure if I can top that. It's always an immense pleasure to hear Rob talk about these subjects. It's incredible. It really brings home, the engineering and the maths behind it all. So it's fantastic. I'm just going to talk about an initiative that we do in ICPC to track faults, track repair times, and look at trends of things that have happened over time. I'll try and do this fairly quickly to catch up a bit of time. So last year we had, well, this is the year before last, because this is last year's presentation. I haven't got the 2025 data yet, but we saw 204 repairs in 2024, which was pretty standard. We've now got a data set going back 17 years. We get the data submitted from the private and the zone maintenance agreements worldwide. So we get to see how things are going. The average notified to departure time for repair is 22.5 days. Add on to that transit time, and you can see most repairs are commenced within a month, and half of them are service affecting. So we see this difference between the shunt fault and the fibre break that's been explained already. The split there is about 50-50. We get the data submitted from all these ship operators, and it's anonymized. So sensitive information about which system it was, the location, that's all redacted. So ICPC get to assess this data in an anonymized form. That means it's not commercially sensitive anymore. Interesting observation about the repair frequencies is that it stayed pretty flat. If you look at recent years, in fact, it started to trend down even at around 200 a year. Yet the number of kilometres of cable in the water, in service cable kilometres, has risen quite dramatically. And what this means is that we're actually getting better at protecting cables. The fault rate per kilometre is trending down. And if we go way back in time to a look back at, when was this, 1873 up until 1914, they experienced on average one repair per 500 nautical miles. So that was 10 times worse than what we see today. So they were doing 10 times more repairs on a length normalized basis. So we've come a long way in 150 years. Repair frequency varies immensely by region, by water depth, by depending on the specific risks. And as you can see from this map, the hotspots are in the darker colours. They tend to be in Asia, around Northwest Europe, and then a few other hotspots around the Persian Gulf, but they're generally in the shallow seas where there's a lot of competing uses of the seabed. Some places have been very lucky. They haven't had any cable faults, not many of them. Iceland, some islands in the South Pacific, Poland, Tanzania, Mozambique, Sudan, they're the lucky ones. The fault distribution between the various maritime jurisdictions, I think you're aware that countries have sovereignty to 12 miles, that's territorial sea. Then you have the exclusive economic zone out to 200, and then beyond that is the high seas. So the high seas portion only sees 2% of faults. So once we get our cables out, far from land, they're generally super safe. And we get slightly more repairs in the Atlantic than we do in other oceans when it comes to the high seas portion, just because it's a slightly more complex environment, as Rob described, with the various currents, the complex ridge system. Fault causes and types. Again, you know this already, but most of the faults are caused by fishing or anchoring. Sometimes you can't determine whether it was fishing or anchoring. You just know that your cable's been mangled. And that comes into sort of the green category, which is with one or the other. And then smaller proportions, 7% down to geological activity, 4% abrasion, and 3% plant failure. And it's quite interesting to compare this with the power cable sector, because in the power cable sector, I understand it's almost the other way round, where 80% of faults are caused by intrinsic issues with the product. On the fault types, as I said, there's roughly a 50-50 split between the fibre breaks and the shunt faults. Shunt faults are great because they give you a bit more time to commence repair and you can plan things. But as Rob explained, it's a ticking time bomb. You never know when that shunt fault is going to burn through. I was asked to produce a slide specifically on the Baltic Sea due to all of the media frenzy around the Baltic. 2024 was a slight uptick, but it wasn't a major departure from the norm. It's just that people had never really got excited about it before. You can see that, in fact, 2008 was, in fact, a busier year for repairs in the Baltic than 2004. So, a lot of, if you drew a correlation between media stories about cable faults and actual cable faults, you'd find there's not a particularly good correlation. This is a new slide, which wasn't actually in my slide deck for the ICPC presentation, but I thought I'd include it anyway for you special people. But it shows faults and repairs in Northwest Europe. You can see the countries listed at the bottom there. And we see such a massive downtrend. 5-10 years ago, we were up at 45, 50 cable faults per annum. Now it's declined right down to 15 or less, which is a massive success story for Northwest Europe. And how have they achieved that? I think there's 4 things. Firstly, we've seen some problem cables retire and go out of service, which is always good. Secondly, we've seen newer cables come along that have been better protected with deeper burial. laid at the right speed and all the rest of it. We also have seen more usage of AIS, so monitoring vessels, trying to contact the fishing boats before they pass over the cables to warn them off. And lastly, we've had some damage claims, and I think the enhanced media attention to cable damage issues generally has made mariners more cautious and acted as a good deterrent. But the bad news story is that the response time to repairs is going up everywhere. And this is not good news for the industry. When I first started tracking this a decade ago, we were repairing cables within 2 or 3 weeks. It's more than doubled since then. And the problem places for slow repairs tend to be either where you've got lots of them happening, so there's a backlog and a queue, or where you've got regulatory impediments such as long permitting times, cabotage restrictions on which vessels you can bring in, or processes like having to import the ship or pay a bond or some duty on the vessel before you commence a repair. A lot of red tape. So you can see the enormous difference here. So in Europe, South Africa, a lot of the Caribbean, we're getting repairs kicked off within just a few days. In Asia, parts of South America, we're much higher numbers. Got my glasses on, I can't even read it, but it's typically 50, 60 days. And in terms of the trends, we see that despite the repair numbers going down in the rest of the world, the delays are still there, indicating that it tends to be the regulatory issue primarily which is causing the problem. And in Asia, that's compounded by the backlog and the queuing situation. We also see more owners opting to do planned repairs where they choose to delay. They might decide that they want to wait for the better weather, and they might have not ordered enough spares to begin with and having to wait for them to be delivered. It might be a shunt fault where it's not traffic impacting and they choose an opportune moment to get that done, which is a dangerous game. And part of it's down to the network being more meshy. There's more opportunities to fail over traffic onto other systems. Most of the hyperscalers and the big carriers, they run mesh networks now that use protection equipment that can flick the traffic between different cables at the blink of an eye. And it's great to have what's a so-called self-healing network, but it doesn't truly heal itself until you go out and repair it. So I think there's a bit of complacency going on here in some cases. Looking at the reasons, again, in more detail for the delays, for those countries where they get a lot of repairs and it takes a long time, it's generally the permitting, the queuing, and the operational permitting delays that take the time. And just to give some examples here, again, it's the importation, the bond provision, cabotage, security clearances, and in some cases sanction compliance. For example, with the Red Sea repairs, a lot of those have been problematic because you've got to apply for a permit, you've got to make a payment, and in some cases that's to a sanctioned entity, which is a big problem to deal with. But there are some good cases where repairs do get done quickly, and typically they're in countries where the repair ship is pre-authorized to go out and do a repair. These countries, they all have, some of them benefit from having a sovereign capability of a repair ship stationed in country, which makes it easy. Others don't. You don't have to have that, but just having a mechanism whereby the crew is cleared, the ship is cleared, and if there's a fault, a bit like with the emergency works arrangement we discussed yesterday with MMO, they're allowed just to go out and do it as emergency works without hanging around. And we're trying to encourage more governments to adopt these best practices. This has been the whole point of the ITU, ICPC Subsea Cable Resilience initiative, which is really trying to focus the attention of governments on bringing in these type of provisions. So that's a summary of what's needed. I think, we've also got this issue where, because the repair numbers are going down so much in Europe and up so much in Asia, even though net it's coming out a wash, it means that we need more ships in Asia to do repairs. And it's not as simple as just saying, well, let's grab them from the Atlantic and move them to the Pacific, because the Atlantic cable owners will be, well, hang on a minute, we could get faults, we could have a bad situation. We want our insurance policy. So you can't just leave an area vulnerable with no coverage. You've got to find a balance between the service level that's offered everywhere, irrespective of the fault rate, and also being able to handle the volume. So that's it. Hopefully I've caught up a little bit of time. Just like to thank again ICPC for supporting this and all the contributors of the fault data. Thank you very much.
Thanks, Andy. We don't really have time for questions. So if anyone has a question, did you have a question?
No, but we could do a question. That's all right.
But yeah, let's catch up time. If you do have any questions, if you submit them via Slido, that'd be good. So next presentation is on sensing cables and future technology from Rosie O'Connor of Indeximate.
Hi, so I'm going to speak a little bit about fiber sensing technologies and how they can help to monitor cable health and condition, and I will try to keep it as quick as I possibly can. So yeah, hi, my name's Rosie O'Connor and I'm with Indeximate. First, a little overview of how fiber sensing actually works. So a little bit like radar, but in 1D along the cable. So we send a beam of light down the cable towards the end of whatever cable. We tend to focus on power cables. Towards the end of the cable, at certain points that will come into contact with some kind of disturbance that will cause it to be reflected or backscattered. The light that we get back, we can pull a lot of different information out of it. The return time, so the time it takes for that light to get back to the equipment, allows us to make a really good calculation of the position of the light when it was first disturbed and reflected. And the sampling rate that you can have is determined by the length of your cable. So the longer the cable you have, the lower sampling rate you can use. The shorter the cable, the more samples you can take per second. One of the great things about fiber sensing is that the most important piece of kit is already present in your cables. So that's quite obvious for telecoms, but many people might be aware that the vast majority of modern power cables also have fibers present in them. The equipment is very quick to install. It's about the size of 1 or 2 desktop computers, so it doesn't take up a massive amount of space in your control room or your fiber room. And crucially, there's no interruption to the operation of the cable to install this kit, and it can continue indefinitely once it's installed. So the first type of fiber sensing technology I'll speak about is distributed temperature sensing. The clue's in the name. It gets you a profile of the temperature of the cable and how that changes in time. So the specs really depend on the type of equipment that you have, but as an example, you could have a 1 degree temperature resolution. You could get a reading for every 5 meters of cable, and that reading would be a temperature that's been averaged over about 10 or 20 minutes. So in the example image here, you can see that this section of cable is buried and this section is unburied. The section that's buried is noticeably higher temperature, and you can keep track of that, make sure it's not going over the maximum permitted temperature for the cable. You can also track over time the effect of the tide coming in and out on the temperature of the unburied cable, because there's a noticeable temperature difference that you can keep a track of. You can also use DTS to kind of experiment with the actual maximum temperature that can be put across the cable. There are guidelines that come along, the specs that come along with each cable, but occasionally you can go over that spec of the maximum current. especially if it's for short periods of time. And DTS allows you to make sure that you're doing that quite safely. And we can also look at estimates for depth of burial. So the next technology is distributed strain sensing. Similar to DTS, but it allows you to get an output of the strain that's experienced by the cable. It's useful in very particular circumstances. So we're talking about monitoring installation and detecting instances of really large strain upon the cable. Because of how the fiber is kind of exists within the power cables, it's something called overfilled, which means that there's more length of fiber than there is of actual power cable. It means that it only experiences strain when the cable is under a significant amount of strain. So it's kind of there for extreme circumstances. And this image that I have here is actually time going down, distance going across, and it's showing a cable being unreeled. So the strain that you start to see on the cable as it's being laid, and as it's potentially under tension after it's been laid in the water. The technology that I'm personally most familiar with is distributed acoustic sensing. So this has a longer range than the previous two. It says here 10-meter spatial resolution, but some equipment that's available today can go down as far to 1 meter. So you can get a reading for every 1 meter of cable in certain circumstances. Distributed acoustic sensing, while it's not a direct measurement of strain or temperature, it can actually be used to calculate the strain and temperature on the cable as well. So it kind of does a little bit of everything. And it has a number of current uses and potential uses. So starting over here on the left is kind of a very immediate example. This is an example of a bit of turbine falling off a wind turbine and into the water. You can see distance along here, time down here. It's very immediate. It kind of looks like a little bit of a splash on the actual image. So it's very useful in those short-term instances for interference alerts, fault detection, and to allow for rapid and really precise repairs. In the slightly longer term, we can look at vessel detection. So if you're monitoring the cable and keeping about a day's worth of data, you can start to actually see the crossing of vessels as they move across the cable. You can calculate speed. You can potentially look at who might have actually done the damage to your cable if you're able to corroborate that with AIS data and the rest. If you collect DAS data and store it really long term and look at trends really long term, you can start to get some really interesting information out. So the diagram over on the far side is actually a year's worth of tidal vibration information. So it's looking at the tidal vibration experienced by a certain cable over the course from about November 2024 to just after November 2025. And we can see certain trends that are associated with seasonal weather patterns. We can actually pick out at certain points specific storm events and look at the disproportionate effect that they had on the cable. So the last one, state of polarization, it's kind of the odd one out. It's different for a few reasons. So first of all, it uses both ends of the fiber, and it doesn't really give you very much spatial information, but it can cover much, much longer sections of cable. So we're talking in the thousands. It works instead of by transmitting the light and waiting for the reflections back. You transmit the light at one end, you kind of receive the light at the other end, and you compare the light that was sent out to the light that was received to get information about what disturbance the cable experienced while the light was being sent along the fiber. This is really good for obviously monitoring very long cables and potentially using some other data to get information on where those disturbances might have occurred. It's also good at collecting information about weather patterns and for earthquake monitoring and detections. So a little bit of an overview. DTS, DSS, DAS, all very useful for a variety of things. One is health and condition kind of long-term monitoring. It can also be used to support other monitoring campaigns, other monitoring surveys, and to support repairs in terms of finding the location of faults, checking the location of a boat as it moves along the cable, and also for environmental monitoring, whether that's vessel noise or whale detection. There's a lot of potential for DAS in whale protection, kind of whale and other ocean mammal detection. The benefits, so it can be used as proof of cable condition when it comes to discussing premiums with an insurance company. It can be used to reduce maintenance costs by allowing you to make much more targeted maintenance and repairs to your cable. In some instances, it can replace more expensive and more intrusive monitoring. And if you do maintain the data, it can be used as a continuous health record of your cable and its condition. So yes, thank you very much. I assume we don't have time for
Okay,
questions.
we have got time.
Okay.
Anyone got a question?
Are you seeing a lot of wind farm owners and asset like power cable owners using DAS like regularly to monitor now? Is that something they're like?
It is increasing. So we're seeing an increase in DAS. We see a lot of people who have DTS kind of running in the background. In terms of ongoing monitoring, we're definitely seeing an increase in people getting DAS on for periods of time. We are seeing an increase in both, to be honest, but we're seeing an increase in people kind of getting DAS on for a period of time, getting an idea of what's going on, and then maybe, just seeing it as like a kind of a temporary thing. But at the same time, we're also seeing an increasing number of people who are getting the kit kind of permanently installed. So in both ways, yeah, I would say.
Anyone else? Steve?
I just wondered if some of your customers have sort of like asked about the inference associated with UNCLOS and the legislation where you are allowed to cross an EEZ as long as you're just doing pure telecoms, you're using the cable for pure telecoms. But obviously with the state of polarization, you can go a lot further. Is anybody generally worried about that might impact the ability to lay a cable across an EEZ if, say, maybe a bad actor, maybe country says, oh, we don't want you to put your cable across because you're not just doing pure telecoms?
So we primarily deal with power cables on much shorter ranges. So we have done some work on telecoms, but we haven't worked that much with state of polarization. I made sure to include it because I'm aware that there's a lot of telecoms people obviously in attendance. So that's not something that we've come up across, but we are a bit more focused on power cables and that side of the industry.
Okay, yeah, thank you.
Anyone else? Okay, thank you. So we're going to move next presentation to after coffee break, seeing that we're quite close to it. So if we can take coffee now and start back at quarter to 12, please.
That one.
What time do we finish? 12:30. Well, we haven't got a finished time. It just says end of virtual link and close of workshop. So
Yeah, I'll give myself 15 minutes.
yeah, we might go over a bit anyway. Okay. Welcome back to the final session, in which we've got cable protection committees around the world from John, cable recovery also from John, cable recovery 101 from Michael Logan, and recycling, reuse, sustainability from Dr. Mike Clare, and then Harriet will kindly summarise at the end of those presentations. And in terms of the finish time, we were aiming for around 12:30. So, okay, I'll pass over to John for cable protection.
Okay, thank you, Clive. And I just wanted to introduce myself to start with. So for those who don't know me, I wasn't here yesterday, and I'm John Rottersley, and I'm one of the directors with ESCA. So very, very pleased to be here. And it's such a privilege to hear from all of our speakers. So thank you to everyone who's been involved. So I'm going to go relatively quickly through the topic. It's a big topic, but we're a bit limited on time. So I'm combining two presentations into one. So bear with me if I skip any slides. So to start with, we've heard through all of the sessions that there's various different risks and threats to submarine cables. We've heard about fishing, commercial fishing and anchoring, which pose the biggest risk as per the presentation from Andy. But then there's all sorts of other things. And we hear from the media about intentional damage and sabotage. Well, that's maybe not the main thing that the industry is focused on. But we have quite a nice horror show of images. I know that Rob and others and Alistair have shared some of them already. But this shows that cable damage isn't necessarily a clean break. It's not necessarily something which happens in a straightforward way. And when armour wires get stripped away, it can cause all sorts of difficulties in terms of repair. So to cover some of the ways that the industry organises and structures itself, there are cable protection committees. So this is the European Subsea Cables Association, which was formerly the United Kingdom Cable Protection Committee, based in Europe. But globally, we also have the ICPC, which is the International Cable Protection Committee, and that looks at things on an international level. International law works with the International Seabed Authority, International Hydrographic Organization, and so on. And then in other regions, there are other regional committees. So NASCA in North America, DKCPC, or the Danish Cable Protection Committee, which covers Denmark and the Baltic, OSCA in Oceania. And then what we referred to last year as an emerging initiative in Brazil is now established as the CBPC, the Brazilian Cable Protection Committee. So that's a really positive thing that these are coming through. And we're often asked what the difference is between the global organization or the ICPC and some of the regional committees. And it's really that international and regional focus. So in Europe, we focus on engaging with European governments and others. And then the ICPC covers things at a global level. As we heard from Rob's presentation, there's good close cooperation on cable ships. And I think that close cooperation is equally important within the industry to focus on the topic of cable protection more widely. So one of the questions that comes up quite often is on charting. Should cables be charted, or should they be hidden from chart so that nobody knows where they are? Well, there's a few pros and cons for this, or I would argue more pros than cons. So of course, it's very important, firstly, to let everybody know where your cable is on the seabed. And that means that to cover those 80% or so of accidental incidents, people will know where the cable is, and it keeps fishermen safe. It means that the location of the cable is known and can be avoided. And then there's considerations around liability and making sure that for other sea users, they're kept safe by knowing how to interact with the cable and where it is and so on. Against, people know where the cable is, but I think that's arguably, looking in the context of all the things which can damage cables, it's better if people know where they are so that they can avoid them. And is this a new topic? Is it something which has come up recently? Here's some minutes from the Cable Damage Committee, which was the precursor to the ICPC from 1960. And it documents the request from cable owners to their national authorities and defence agencies to ask for permission to chart cables, because in the post-war period, there were a lot of hits from other sea users from anchoring and fishing. And so really it was seen as a real positive to chart cables to make sure that others could avoid them. And there was a lot of interaction with defence departments, NATO, governments, who were really interested in the topic. So there's a long history of engagement on this. So the technology has changed in terms of the way cables are installed, what they do, and so on. But actually the principles for cable protection remain the same. And we've heard a lot about burial, improved burial practices, maintenance, and so on. So safety, I've already mentioned, it's very important to make sure that everybody is kept safe. And so following some incidents in the 80s and 90s, where some vessels snagged submarine cables and they resulted in loss of life incidents, the KISCA project, which was set up, which is the Kingfisher Information, I've forgotten the abbreviation of KISCA, but we'll come to that in a second.
Information Service Offshore
Yeah. So there we go. So there we go. That's helpful. So this was the precursor to KISORCA, which, as Clive says, is the Kingfisher Information Service Offshore Renewable Cable Awareness Project. But KISCA was set up in response to safety incidents and was designed to keep fishermen safe and make sure that they know where cables are. So charts were produced, they were sent out, and port tours conducted to make sure that people can operate safely around submarine cables. And now we have KISORCA, which was established in 2012, and that brought in renewables, power cables, telecoms cables, and has all sorts of interactive elements to it. So I won't go through in too much detail, but I'd encourage everyone to visit the KISORCA website, look at the snagging protocols, the emergency procedures, interact with the interactive map, and you'll see that there's emergency hotlines that those who might be snagged on a cable can call, and it's a really positive project, which is well respected by the fishing industry and the cable industry as well. So then there's also the Kingfisher Bulletin app. I'd also recommend visiting the website and taking a look. So you can sign up for real-time hazard alerts, which will come by text or email to your phone. So if there's a cable repair or some cable work taking place, or maybe a new exposed area or something that needs to be sent out as a safety message, this can reach other sea users really quickly and effectively. So it's a really positive mechanism. And I will pause there, and I'm afraid you have double me because I'm moving on to the next presentation on cable recovery. So maybe I'll pause for a question if there's any, and then otherwise move on. No? Okay. So otherwise, I'm going to considerations for cable recovery. So this starts the next section of the Cable Awareness Workshop. So we're closing with myself talking about some of the policy considerations for cable recovery and the industry perspectives. And then we have Mike Logan is going to give Cable Recovery 101, talking about the practical elements. And then we will close with Mike Clare talking about recovery, recycling, and some of the circular economy considerations around cable recovery. So the current situation, to give an example, in the UK for cable recovery in terms of licensing, for installation in UK EEZ, there's no licensing structure to install or repair cables. And this is because of the provisions of UNCLOS, which has been mentioned a lot through the sessions. And within the Marine and Coastal Access Act, UNCLOS is enshrined. That means cables can be freely laid and maintained subject to certain provisions. So that's true for linear cables or power cables and telecoms cables, with some different considerations for offshore renewables. The regulatory processes vary a lot across Europe. Some states mandate recovery at the end of service. Some have a looser approach, and it can be considered on a case-by-case basis. And so decommissioning is certainly a hot topic. And the industry position in the past has always been consider on a case-by-case basis whether there's going to be a bigger environmental impact from recovering a cable at the end of service, or whether it's better to leave it in situ. And I think often, because the low impact and cables are chemically inert, they're pretty benign on the seabed, even though there's maybe a small disturbance from lifting it back up again to recover at the end of service, it's been seen that impact might be higher. However, there's a lot of offshore development. There's a lot of things going on the seabed, and there's a significant number of cables which are out of service. So whether that applies to this day is still something to be considered and explored, and I think there's not a concrete position on that yet. There's been discussions on compensation for development of offshore wind and development of other activities, and recovery of out-of-service infrastructure has been discussed as part of that, and might feed into the principle of marine net gain, which again, I won't go into in great detail, but I encourage everyone to go away and Google what marine net gain is. It's a consideration for enhancement of the marine environment to leave the environment in a better condition following a project development than it was prior to it starting. So it's a slightly different thing to the compensatory processes. And then, as Mike's going to talk about a bit, there's all sorts of considerations around recycling, sustainability, zero waste economy, and so on. So just to cover the UK situation, as I mentioned, for installation and repair, they're subject to freedoms under UNCLOS, and that's enshrined in the Marine and Coastal Access Act. And I think yesterday, hopefully you heard about the MMO and the processes that followed there. But in the UK, there's a slightly different consideration for cables in exclusive economic zone, and it is a licensable activity. And so there's no obligation for cables to be recovered because of some of those freedoms, but licensing presents a potential barrier for that recovery taking place. Within territorial waters, the Crown Estate obviously leases the cable, and so there's incentives there for cable recovery at the end of service. And then across Europe, there's all sorts of different considerations on how cable recovery is thought about. So I think it's helpful within the cable protection committees, within the industry more widely, that we develop our own policies and positions on what that means and whether cables should be recovered, left in situ, etc. And that's an active dialogue within the sector. So within the UNEP WCMC 2009 report, Submarine Cables and the Oceans Connecting the World, I know you heard from Izzy on data and evidence, and hopefully a lot of these publications have been shared throughout the sessions. It notes that the removal of cables should be evaluated on a case-by-case basis. And I think this is a good position, but quite a blunt position, which doesn't reflect necessarily a lot of the nuance that might apply today. So then there's been an updated report in 2025, and that's Submarine Cables and Marine Biodiversity, which was a collaboration between ICPC and UNEP WCMC, and that considers the position further again. And then there's been new research published in 2025, which I think has probably already been noted, and Mike will probably talk about in his section, which then gives some builds on the evidence base for cable recovery. So again, it's an evolving topic, and I think it's something which is a really good thing to think about when decommissioning in the marine environment is such a big hot topic. So some of the legacy challenges, there's obviously a lot of cables have been installed since the 1850s. There's telegraph cables in all sorts of condition. Out of service cables aren't abandoned. They are the responsibility of the cable owner until such time as they're recovered. But of course, for new systems going in, there'll be sections recovered through root clearance. And so shorter sections will remain over time. And when the exclusive economic zone is then subject to a lot of development and offshore wind and other things which are being thought about, it might be better to think about recovering longer lengths and considering the licensing or other barriers, regulatory processes that might be in place. This is something we're actively engaged upon. Then in terms of compensation or net gain, I think I won't go into this in too much detail, but again, it looks at whether there's a better case for leaving cables in situ or recovering them. In terms of benthic impacts and impact on the seabed, I mean, it's maybe not such a strong argument. So if you look at the case for removal, the disturbance is quite small, but it's probably higher than leaving the cable in situ. But that's if you view the subject in isolation. But then if you look at future development and the challenge of leaving shorter legacy sections of cable, then maybe you might think that recovering longer lengths is more important. And then as you consider the further developments over the next decade or longer periods of time, then you start to need to think about this in a bit more detail. And I think I will finish there. So if anyone has any questions, happy to take them. Thank you.
Hey, any questions for John? Any on Slido?
What can the cable industry learn from other seabed users or even from air and land about raising awareness of infrastructure to avoid accidents?
Sorry, repeat the question.
What can the cable industry learn from other seabed users about raising awareness of infrastructure to avoid accidents?
Yeah, so I think there's a lot of cooperation between different sectors. So there's the FishSafe platform for oil and gas, and then the cable industry has had very good success with Kiss Orca. And I think that's why we promote it so strongly. So the primary aims of ESCA are to protect infrastructure, but also to promote maritime safety. In terms of what other sectors do, I think there's a lot of engagement between FishSafe and Kiss Orca. I think we're doing pretty well there.
And another one, where disused cables cause maritime safety incidents, where does liability sit if the original operating entity no longer exists?
That's a good question, a very difficult question, not one I think I could answer very easily. In terms of most infrastructure, it's important that it remains chartered. The ownership and responsibility for cables which go out of service remains with the cable owner. For older legacy systems, someone cleverer than me might have to answer that question.
I think one of the issues that's, well, quite a big issue is that some of these companies go into liquidation. So there's no one to talk to about the cable at all. So whether you go over the cable is I don't know, but it's a big issue because there's lots of cables on the seabed that don't have any owners whatsoever now. So the liquidation. Anyone else?
I don't think you need to do the microphone.
I'll repeat it.
You might do for people online, so I'll give you anyway.
Yeah, I've actually been involved in a case where the owner had gone bankrupt and we're looking to repair, and we actually went and spoke to the receiver. So if you have that option open to you, you can still do that. Also, some of the legacy telegraph cable is owned by previous conglomerates that got absorbed by, big telco companies. So technically, you could go in that route as well if like obviously BT and Cable and Wireless, bought up a lot of the old telegraph or were merged in. So there is some liability in that front as well. But it is very difficult. Trying to find somebody to pin them down. It's difficult.
Okay, time for one more. Anyone? Okay.
Oh, Clive.
Has there been much research into removal of cable protection, like mattresses or rock?
I don't know if there's been a lot of research on removal or decommissioning of cable protection, but it's certainly, in terms of published research papers, it's certainly a hot topic of discussion as to feasibility, what the capabilities might be. We have a renewable and power subgroup in ESCA, which is considering exactly this topic, looking at what the options might be, maybe considering some research in the future. So I think it's a developing topic, because as all of this infrastructure is developed, thinking about how it's decommissioned is really vital. Thanks.
Okay, thanks, John. Okay, next presentation is on Cable Recovery 101 from Michael Logan of Mertec Marine.
Cool. Thanks very much. So we've heard over the last sort of day or two and seen some examples of cable recovery when it comes to repairs. So most of my presentation is going to be some pictures and just some videos to put a bit more context into that, which probably need to turn the volume down for, because it's got some really terrible music overlaid with it. So obviously the cable recovery has been happening since about the 1850s, obviously when the new systems at those times were going in. Quite often shore ends would be lost or they'd be damaged, so they needed to be recovered. I think Chloe mentioned it yesterday, the 1868 or 67 cable, the first transatlantic system was installed. But actually, it's probably the first case for a deep water recovery. So in 1866, they went back to recover the cable that was lost in 1865. It was about 4,000 meter water depth. It took them many weeks to try and recover it. They actually managed to remember exactly where the cable was, quite remarkably. They did successfully recover it and recovered about 2,000 meters approximately. I wasn't there, so but I've heard. So yeah, that was probably the first case, and probably quite an important part of the industry to say that this can be done. It's proven, and there's a case for doing these type of systems going forward in the future. So we heard from sort of Rob earlier. He was talking about, when you're in the Atlantic or in the middle Pacific, you want to get out as soon as possible. You don't want to be bobbing around there too long doing a repair. So take a moment to think about a crew where our business model is to go out and spend as much time in the middle of the Atlantic and middle Pacific recovering cable on a much smaller vessel than the typical vessels you've seen over the last day or so with the DP and the ROVs. This vessel here is one of our vessels. It's the Unique. It's 66 meters. So you imagine that, being in the 8-meter waves, not much around you. Yeah, so a moment for them. So like most people in industry that we've heard over the day or two, the founder of our company got in it purely by accident. He was a farmer. So very different to being out at sea. He went to auctions like you did as a farmer back in South Africa quite regularly. And he saw this piece of cable being auctioned, and he saw it and thought, wow, this is fantastic. It's like a gold mine down at the bottom of the sea, is it? Had no idea. So actually the first vessel I think Mertec Marine got was an icebreaker vessel, because they had the idea of, let's use the icebreaker and then maybe we could recycle the cable on board the vessel. So I think there were some nice examples shown earlier of the cable, quite small, thin, compact. But as soon as you start stripping that cable, the volume suddenly increases tenfold. So that didn't work. Here we are today. Going back to the recovery at sea, So we're quite thankful for organisations like ICPC, ESCA and others, where the data is shared. So before we go out to do a cable recovery, we do a cable recovery plan, telling everyone about where we're going to be, what we're going to be doing, just to make sure that everyone's aware. So any new systems going in can be accounted for or not charted yet, because there's a few people in this room would be quite upset if we was to recover their new shiny system. So what we did first, we can pretend this is the transatlantic I was talking about earlier, but it's cut and run. We cut the cable. I think Alistair had a nice picture of the grapnel that was used to do the cutting. I've got one later on in the presentation. We do the cutting, and then probably about 1.5 meter water depth away from the cutting, we do a hold and run, and you begin recovery either side. There we go. That's a zoomed in version of the grapnel that Alistair showed earlier. So there'll be people on the vessels. We're lucky enough that we do have a little bit of technology, so we can see when the tension rises. So if we have a nice long tension rise, it probably means we've caught the cable, and then it drops off and it's been cut. If we've suddenly had a big increase in tension and then it's gone down, it probably means you've just hit some rocks or the seabed features, and there was nothing. So when the grapnel comes up, we'll also inspect the grapnel to see what damage or information we can find from it as well, because it gives us a good idea. So I think you saw these earlier. So we use these to hook the cable on the hold and run. I think this should be a video if it plays. No. Oh, no, it's not. This picture. So here you can see the cable was caught. It's a terrible example to show you because actually the cable got caught on the shackles above the grapnel. So it's pure luck that we actually got it, but I thought I'd just show it there anyway, because you can get a bit of luck during cable recovery. And then like our vessels, so as I said earlier, they're sort of 66 meter length. They're ex-cargo vessels that were converted. So they were actually used in the industry for many years as cargo and cable around to different locations. So they've got cable tanks and everything else. This may be the video. There we go. Got rid of the music. Sorry. Yeah, so you can see the cable coming up there on the hold and run. And coming through. Okay. I think this is just another view of the similar sort of thing. So I'll skip through that because of the time. And then obviously when they first recovered that cable back in the 1866, they used grappling, and the methods haven't really changed to today. Obviously the tonnage pool we've got now is more than they had back then. They were quite worried about the tension when they were trying to recover the cable back in 1866. I think they had a couple of vessels out there trying to support it at the time, and it's slow. It was a slower recovery. So our vessels will recover about 45 to 60 kilometers of lightweight cable a day. We obviously are picking it up to recycle, so we don't worry about the fibre optics or anything in that being damaged so much. It's not being reused. And there's also other techniques where we've adapted over time as an industry that can help support picking up cables. So I think I've got an example here of an ROV being used off of one of our recoveries off the coast of the US. Again, I'll have to pause the music. I'll keep it on. Makes it more dramatic than it is. So the ROV just cuts the cable and it hands it to the cable recovery vessel, which will then recover the cable. It allows us to get a bit closer or to do recovery in areas where you can't really grapnel because the other cables may be too close to it. It can be a lot more precise, very precise. And then just to sort of close the loop, I guess. So you would have seen on earlier maps over the last day, so you've got the cables going across the globe. But the maps we've actually been shown over the last day and a half is probably only the in-service stuff. So it's the last 25 to 30 years of installation. So, we've been doing this for 150 years now. So add an extra 120 years worth of cable on top of that, you can see how it's getting quite congested. Although they have quite a small footprint, the distance you need between two cables is quite vast and makes it difficult. So when we recover cable to clear up routes and things like that, we don't just recover it and just dump it and it goes nowhere and we forget about it, it goes into landfill and creates other problems. We started recycling the cable. So just to give you a quick close of the loop, this is actually one of our factories in South Africa, so where the cable is recycled. So I won't go too much into detail, but you can see there where it's, I don't know how clear the pictures are, but you see some of the manufacturing lines down the bottom. So if any of you have been lucky enough to see the cable being made, we're pretty much doing it in the complete opposite way, reverse. So we're just stripping it all down into its various initial components. So the polyethylene, the copper and the steel and things like that. And to give you an idea, the cable's been reused. So it gets used into wire rope. It goes into a lot of the South African vineyards, fencing, things like that. If any of you own Volkswagen cars, a lot of the screen wash units are made out of, the polythene's made out of submarine cable. Yeah, that's pretty much it from me.
Okay, thanks, Michael. Any questions for Mike?
And so are you, when you're making, basically is your revenue profit coming from the recycling? Are you tendering to go out and recover the cable? Yeah, sorry. Yeah, so are you, is your revenue coming from the actual recycling, or is it from going out and tendering to do the recovery for a client?
Yes, it's a very tight business model, as you can imagine. So we're just, I guess, scrap metal guys on a large scale. It's the recycling element of it that for us, that is where you get a bit more profit. The ships are expensive going out there, which is why we can't use the nice sort of vessels that Subcom, Global Marine, ASN, and those types of company have. We have to be a bit more innovative and use the smaller cargo vessels efficiently. So everything that we do has to be quite efficient to realise that. Yeah. Okay. Oh, sorry.
Is this working? Yep. Is it a viable business model locally? And for example, with the car components, do you need an agreement with some other type of manufacturer to make it scale?
Yeah, that example is that one of their main depots is in South Africa, so it's local to where our factory is, and there's no huge costs of shipping around the world. The material. So yes, there's local solutions, but we can recycle in other locations. We've got a pop-up facility. So if we think one market could be doing better, or there's a need for a certain material, then we could recycle more locally to make it more cost-effective, environmentally friendly.
Okay, last question.
Yeah, Mike, I'd just like to say you're obviously aware, but I was lucky enough to go to your facility back end of last year, and I have to say how impressed I was at the facility and the fact that many of the dismantling tools have been bespoke developments within the factory. But also what I was surprised to learn is that you've moved on, and not only do you recycle the submarine, but you also do all the electronics.
That's right.
And that was particularly interesting to see the recovery of all the rare metals. So yeah, that is something I think to be proud of. It's fantastic.
Yeah, thanks. Yeah, as you know, there's many repeaters and stuff connected to the cables, which we fully recycle as well.
Okay, thanks, Michael.
Thanks. Thank you.
So we come on to the last presentation, last but not least. Recycling, reuse, sustainability, Dr. Funke.
Well, I haven't got any inspirational walk-on music like Mike. I feel quite disappointed. I'll have to do that next time. I appreciate I'm the last one on, so hopefully you're not flagging. But thanks to John and to Mike, I think, really for setting the scene here. And I guess this is thinking about end of life of systems. It's the end of life of this workshop. It brings things to a close and hopefully wraps things up quite nicely. If we think back to the presentation that Izzy Yo gave yesterday, thinking about the importance of data for informing decision-making, the importance of peer-reviewed evidence, and discussions happening across sectors and outside of the sector with other stakeholders. I think this topic really covers all of those areas, but it's, as Mike said, and as John has said, it's really an emergent area and it's very much a hot topic, both from a scientific study perspective, but also from an industry perspective, a marine spatial planning perspective. So as Mike had said, there's an awfully large number of cables that lie on the seafloor. In service, something over 1.8 million kilometers of fiber optic cables. But if we go back into different eras, or we think about of service fiber optic cables, we look at telephonic coaxial cables and all the way back to telegraph cables. Adding that up gets to something above 3.5 million kilometers of cables, of which 1.8 million kilometers is in service. So an awful lot of legacy infrastructure that still remains on the seafloor. I don't know the numbers. Mike probably has a better handle on what's actually been recovered, but it's a relatively small number when you stack it up next to these. You've seen from Rob's presentation and others the sorts of types of cables that we see on the seafloor. Mike talked about kind of the mechanics of actually doing this and that there is a kind of commercial model there for it. This slide's really talking about the drivers. Why do we want to potentially recover and recycle cables? So one of them is this environmental and social imperative to get towards a zero waste or a circular economy. In some cases, it's not truly circular because you're not always reusing cables. Rob talked about an example of an old section of deep water cable being repurposed as a festoon type system in the Caribbean. But in other cases, it's being used for other purposes. So it's not being used to make new cables, but it is being repurposed to make fencing components for cars, these sorts of things. So we'll call it a zero waste economy. But it's worth putting in mind, I guess, the reason why there's an increasing consideration and interest in recovery and then recycling of cables is by a number of other drivers as well. One of these is spatial squeeze. We need to free up real estate on the seafloor for the laying of new cables. And this is useful from a sustainability perspective because it means you're not laying cables in areas that are maybe previously unaffected. Coming back to Andy Palmer-Felgate's presentation, thinking about the identification of resilient routes, it provides the opportunity to remove cables from areas which are known to be safe areas to lay cables, and you can relay cables there. Commercial imperatives, in some cases, there are contracts, there's regulatory drivers that mandate the recovery of cables from the seafloor. There's a whole raft of different drivers. So it's not solely from a social and environmental perspective. And in many cases, it will be regulations, it will be commercial reasons for recovering those cables. Mike's shown some really nice images and videos of the operations that are actually involved. And they link also to many of the operations that have been talked for recovery and repair. The question that John asked around, is it better to leave cables on the seafloor or better to recover cables? I mean, the answer to that really is very much it depends. And we need to step back if we're thinking about sustainability and we're thinking about all the other aspects within this industry. We need to consider everything together. So it may be that just on its own, as John said, it will be environmentally most considerate to leave the cable on the sea floor. But if it's freeing up an area for a cable to go in, that's not going to have to go in another location, if it's contributing materials to a circular economy, then these things need to be considered together. I presented this last year, and since we've published the first peer-reviewed paper, which really looks at the environmental considerations for decommissioning subsea cables, primarily focused on telecommunications cables. John has talked about different publications, particularly the United Nations Environmental Programme report that was published last year. And in that really talked about where is the peer-reviewed evidence about environmental impacts or interactions associated with this industry. And there's a huge amount of peer-reviewed literature, but we identified that from the perspective of recovery of cables, from Telecom's perspective, there was nothing. So we're keen to make sure we contribute to that literature. What that needs is data. And so we've benefited really from data which has been shared by Subsea Environmental Services, by Mertec, and by others who are actively involved in the recovery and recycling of cables to say, can we identify what the actual impacts are? So we've done that work, and I'll point you to the paper at the end and just some headlines of what it is that is causing environmental impacts associated with recovery. Obviously, there's the impact of grapnels, but as you've seen, grapnels are pretty small. They penetrate the seafloor relatively limited, tens of centimeters maximum, and are maybe being dragged once. In some cases, multiple drags may be required to find the cable. Where cables are buried when they're pulled out from the seafloor, that there may be some local disturbance of sediment plumes which are generated, but footage from remotely operated vehicles shows that this is very localized and short-lived in duration when it does happen. And where cables are buried to an excessive depth, we're talking below 1 meter or 2 meters or so, typically cables are then not recovered. There'd be no sense in having a mass flow excavator to come and get that cable out unless there's a real imperative for doing it. And that would have too large an environmental impact to really be considered. So the conclusion of the study, and I'll point you to it later, but which includes seafloor video observations from cables that are being recovered, photos of those recovery operations and video, demonstrates that the impacts associated with cable recovery are very localized and very short-lived, and typically much, much smaller than the impacts that would be involved in the installation, and even then have been identified to be quite small. One of the questions that has been asked, and I guess people from this industry really like to show photos of corals all over cables. They like to show all sorts of charismatic organisms interacting with the cables. But what that's done is it's kind of steered a perspective and a view from a lot of people who look at this that say, well, every single cable must be completely covered in animals. So these are local habitats, which they can be, as shown on the right-hand side of these slides. These are some cables in some very biodiverse environments offshore British Columbia in the Mediterranean, in the case of G for this coral-encrusted cable. And then F is some examples that Izzy showed from systems in California. But the question that I was faced with was, is this the norm or is this the exception? And then start seeing photos like those in A, B, and C. And these aren't cables which are being spooled out to be installed. These are cables that have been recovered that are then going to be put forward for recycling. So from Mertec and Subsea Environmental Services. And these cables are pristine. And they're not colonized. They don't have organisms over them. And so what we've started doing is working with cable recovery companies and acquiring footage, photos, information, observations, starting to gather data in a systematic way to say when and where do you see colonization of these cables and where don't you? And just one example, recovery of almost 2,000 kilometers of cable from the North Atlantic offshore Portugal found only one stretch of cable about 2 meters long that had any organisms attached to it, and the rest of it was completely pristine. I think Mike would probably agree. If his cable looked like it did in G on the right-hand side there, you wouldn't have a business model. You'd have a back deck that was pretty much just full of corals. So actually, since the 1870s, people have been proposing more systematic recording of biology during cable repairs and cable recovery. So we're moving forwards. I think we're moving forwards much faster now. The image in D shows cable being recovered. I can't even remember where that was. I think it's offshore Jamaica. watched through several days worth of this video to see, do we see any organisms on it? Somebody else was doing the same job as this. There's, I think it's a shearwater, so a bird that sat on the gantry crane, watching excitedly, thinking this is the long line that Rob was showing in his presentation, waiting excitedly to see a fish, and then it does, but it turns out to be a repeater-shaped fish. So the fish is very disappointed, but it's doing a very good job for us, that we would have a biologist at sea doing the same thing. So we find actually that most of the time, 99 point many nines, the colonization of cables is nil. But it is helpful to understand locally where we do see colonization, because these are areas maybe which are biologically much more interesting. It's worth stressing, I think, that in some jurisdictions, some regulatory guidelines, there's a mandate to recover all lengths of cable. And in some cases, this is interpreted as also being sections which might be horizontally, directionally drilled as well. But it's not always possible to recover all lengths of cable. And I think that's important when we start thinking about decommissioning plans. In cables that are excessively buried, where, say, sand waves have migrated over the top, underwater landslides have stacked meters worth of sediment, it simply isn't possible. And if you were to go and get that cable, the environmental impacts would be excessive. In some jurisdictions, Singapore is one example, there's a mandate to bury cables to, I think, more than 8 meters depth, maybe deeper than that. There may be physical protective structures which are put in place, which may become colonized. And in some cases, these physical protective structures are being designed so they enhance the local biodiversity. So it may not make sense to recover that. And certainly where you have cable crossings or pipeline crossings and you have legacy infrastructure or infrastructure which overlays your cable, you don't want to recover that. So it is important that there are many, many considerations which will warrant leaving some cables or sections of cables in place. And as John said, it's not that useful to say, we need to take a case-by-case basis. We're pulling together information about different scenarios, but within that, understanding context is important. This means environmental context, and it means all the other contextual information as well. So in many cases, it will be more sensible to leave cables in place or sections of cables, but there really are opportunities here from an environmental perspective. But understanding that environment is critical. And then many other options for recovering out of service cables. It's not your stomachs that's going, it's not nearly lunchtime. This is the sound of a blue whale offshore Oregon that was recorded on a fiber optic cable. So using approaches like distributed acoustic sensing, distributed temperature sensing, state of polarization, we can make fundamental scientific observations that help us understand the biophony, so the noise that's generated by cetaceans, and you can detect feeding calls. You can detect the male, whether it's a male or a female whale. So there's potentially use of I'll stop that whale now. Shush. There's all sorts of opportunities there in terms of thinking about future conservation, future understanding of the ocean. We have projects ongoing here where we're using fiber optic sensing to listen to seafloor currents and potentially detect how they're changing in response to climate change. So scientific opportunities also exist with out-of-service cables, which might mean there's value in leaving them in service. And this technology really is exploding at the moment. I guess if I leave you with one thing from this presentation, and I guess my thoughts, this is quite strongly biased, but based on the past few days, is cables interact with the marine environment. It's really important to understand the marine environment. I think Frankie said, you can't beat nature. Agree with that. We need to work with nature. And to that end, also thinking about the impacts that this industry and these sectors have on the environment. I think this is an industry which is really and has always been thinking about the environment. Some of the first scientific observations and understanding we have of the ocean, that we know there's a mid-Atlantic ridge, is because the cable route got shallower in the middle of the ocean and then got deeper. So in the 1850s, we were discovering that there's complex life in the deep sea. So we continue to learn about the ocean. But if we're thinking about what we do to the ocean and the decisions we make, we need this broad holistic view of sustainability. We shouldn't just be thinking about carbon emissions, shouldn't just be thinking about a circular economy. Many aspects of sustainability are not easy to quantify with metrics. So it's critical really that I think this industry, it's important that you identify knowledge gaps. And when you're uncertain about an environmental interaction, have discussions with academics, have discussions with policymakers, have discussion with the Crown Estate and others, and work out how we should fill them. That peer-reviewed evidence base is really, really critical, and it requires input, that ultimate decision-making from academic research, industry, policymakers, and it's why I think events like this are so important. If we're going towards what we hope is a sustainable future for this industry, then this cross-sectoral dialogue is absolutely critical. If you want some bedtime reading, there's a paper here. I encourage you to read it because I think it's got some useful things in there, and we're also glad for any feedback. So I think from me, thank you very much. We are very, very glad to have had you all here at the National Oceanography Centre. It's a pleasure to have you here, and thanks for the discussions over the past few days.
Any questions for Mike? No.
There's one there, I think, from Matt.
Yeah.
He's going to make you run.
Yeah. Have you had any experience of decommissioning cable protection, say rock protection or split pipe or similar, that in the environment?
No is the answer. And in terms of like peer-reviewed studies, there's also an absence of that there too. So if there are examples, when people have encountered this, it would be really valuable to share information data from that. But at the moment, I think there's a bit of a dearth of that. There's a lot of literature now on kind of building and designing nature inclusive designs as opportunities, but I haven't seen anything from a peer review perspective on recovery of protective structures.
Okay, thanks, Mike. Okay, that's all the presentations. Just a summary from Harriet to close today. List of presentations.
So in the aspect of timekeeping, I'll just summarise kind of the last ones that we've heard all together. Firstly, we heard obviously the presentations that were focused on the one simple objective of reducing cable damage and limiting its impact when it does occur. What comes through clearly is that protection is not achieved by a single solution. It's the result of many small and practical measures, and all of these have to work together in harmony. One important point is the value of knowing how quickly to repair and how realistically this can start. And as Andy showed, the global analysis of repair time showed wide variations between regions and systems. Vessel availability, distance, permitting, and weather all influence the response speed of this as well. This matters because it shapes how we think about redundancy and spares and overall network resilience. In short, understanding response capability is a key part of understanding risk, especially as response times have doubled in recent years, as we heard. Another key takeaway is the continuing importance of accurate cable chartering and monitoring. And when cables are correctly chartered and clearly visible to mariners and people at sea, the risk of accidental damage from fishing gear and anchors can be reduced. Monitoring systems add yet another layer, helping operators identify unusual activity or potential threats near the assets, like the Kingfisher app is helping to do. These are proven, relatively low-cost measures that quietly prevent many accidents before they even happen most of the time. We also heard about the fibre sensing cables and the emerging technologies that offer a more proactive approach. Technologies such as the distributed acoustic sensing and temperature monitoring that Rosie discussed help provide early warning of the third-party interference or developing faults. While not yet universal, they do really point towards a future where operators can have much greater visibility of what is happening along the routes in nearer real time. And it's also a benefit to other disciplines such as environmental monitoring. Finally, the role of the cable protection committees remains central, as John had said. These committees bring together cable owners, fishery organisations, regulators and other stakeholders to share information, resolve issues and promote good practices. Their strength lies in cooperation rather than regulation alone, and I think that's a really key point that we should all take away. Where they're active and well supported, cable damage rates tend to be lower. To conclude, for that part, protecting subsea cables depends on understanding exposure and response capability, making cable information both visible and and accessible, using monitoring and sensing to move from reactive to a more proactive approach, and maintaining strong collaborative forums for doing so. And I think if we focus on these practical actions, we reduce faults, shorten outages, and improve the resilience of the network that all of us highly depend on. So moving on to just the last couple of summaries from the presentations we've just had, in terms of what happens when subsea cables reach their end of life service and how recovery is planned and executed alongside maximising recycling and sustainability. So I think the first key takeaway from that part is the end of service planning always starts much earlier than the actual end of service, funny enough. Decisions made during design, route selection, burial depth, and protection influence how feasible recovery will be just decades later. Cables that are accessible, well documented, and installed with future removal in mind are always significantly easier and safer to recover. This reinforces the idea that decommissioning is not a separate phase, it's actually a part of the asset's full life cycle. Do remember that there are real pros and cons. We heard about legacy issues, we heard about project compensation as just a few examples among many. We also heard a practical overview of how cable recovery is actually carried out. Recovery requires these specialist vessels, grapnels or ROVs, many. Careful tension control and well-defined procedures avoid damaging the seabed and the surrounding infrastructure. Conditions such as water depth, seabed type, and cable condition all affect the approach, which then will go into the cable recovery plan. What comes through clearly is that recovery is a proven activity, but it still requires really good planning, experienced contractors, and realistic schedules. Strong messages from these presentations showed us that there is a growing focus on reuse, recycling, and sustainability, as Mike mentioned. Recovered cables contain valuable materials, copper, aluminium, steel, polymers, to name a few, and where possible, maximising recycling rates reduces waste, lowers the need for materials, and improves the overall environmental footprint for projects. But in some cases, components or equipment can be refurbished or reused, extending the value beyond the original project. These considerations are becoming increasingly important in our day and age for regulators, investors, and even the wider public. But we do need to remember that these are, as we heard, localized and often short-lived, just a caveat. The presentations are also underlining the clear regulatory frameworks and early engagement that are essential. And I think tying back to yesterday, something that's also key to consider are the permits. Sometimes they're covered for these cable activities when we're trying to recover them. And there are expectations around the environmental protection factors and waste management, and these will continue to increase. So early dialogue with the regulators will really help define acceptable approaches and avoid any delays that we all hate in the process. So overall, if we continue to approach end of life in this way, we're going to meet regulatory expectations and also strengthen the long-term sustainability of our subsea cable industry, which is what I think we're all aiming towards. So thank you very much. I'll leave over to Clive to wrap up, but thank you for having me.
Okay, that's it. A fantastic couple of days. Obviously, thank you to all the speakers and for the NOC for hosting us. But to close the workshop, I'd just like to hand over to the ESCA chairman, Steve Holden, who's going to come up and say a few words.
Yeah, thank you, Clive. I haven't been able to get to one of these for a while, actually, but as the chair now, I had an excuse to justify coming. And I have to say, it's been fantastic. I hope you've all enjoyed it. Have you enjoyed it? Yeah. Good. I have to say, on a personal level, many of you know I've been in the industry not quite as long as Rob, my hero. But the quality of the presentations that you've seen today and yesterday are at the top notch. You will not get anything any better in terms of knowledge or education about the subsea industry. So hopefully, well, we are going to do it again next year, aren't we? So if you've got any friends or colleagues who are interested, please tell them to sign up and come along, because I'm sure it will be at the similar high standard as you have witnessed over the last day or a couple of days. Made me feel quite proud, actually. You know, it's a very slick machine, I must say this, and I need to thank in particular for the event Claire, who, as we heard earlier on, had a lot of issues with our friends at Microsoft, challenge the ability to run a successful workshop. But yeah, maybe, yeah, absolutely, yeah. But all the senior senior leadership team of SCARE, you know, I have to shout them out. There's a tremendous amount of work goes on in the background, not just with, you know, conferences and workshops like this, but the general day-to-day, the interaction, and you know, I'm very lucky that I get to benefit from that. I almost like jump on the cycle and so there's already somebody cycling along, making it very, very easy for me. So thank you to all the leadership team. Also, just to summarise, I know we've said it a few times, but it is important that we thank the North Subsea, the Crown Estate Scotland, Suboptic, for all the prizes, and a little thank you also to all the next gen people, those that have been involved. We as an industry identified 5 or 6 years ago that, you know, that we were aging, as Rob has alluded to, and that we need to get more people involved, and this is one aspect of it. Next gen's been another, which I think has been very, very successful. So just want to say to everybody, keep up the good work, and thank you very much for allowing me to be your chair. Thank you.
That's it.
Recording stopped.
Right, let me just